All right, so I think most everybody's here. So I added a few slides to the data I/O because there was a lot of questions and it's relevant for your homework. So they're at the very end. More ways to save. I think that's like a Geico thing. Ways to save. I don't know. So there was a lot of questions yesterday. Are there like Stata has DTAs, like SAS has SAS and BDATs, how SPSS has save files. Are there R files? The answer is yes and no. The answer is yes, but they do not have to contain. Many times they don't contain only data sets. They can contain anything that's an R object. So the way you can save something to disk from something in memory is the save function. So here I just define, x to be some vector 5, right? Just the number 5, it's fine. Also, just note really briefly, you can put semicolons at the ends of lines. You don't need to in this language, but you can. It just says this is the end of that statement. So I have x, and then I have yts. I'm going to read in, using the read CSV function, this long URL, right? So johnmichele.com, whatever, in the data folder, that data we read in yesterday. And we'll talk about some of the syntax a little bit later. I'm just saying I'm using the read CSV function from the readr package, and I want to paste this string together because it's way too long on the screen. So I just wanted to make it into 2 lines so you could actually read what I was reading in. So now we have yts and x in memory and R. And now let's say, hey, I want to save those out to disk. You say save, and you start putting the R objects. So in this case, yts, x, you could have put, 5 to 10 other things. You could just put one thing in there, and then you say the file is equal to the file name. So the save command saves a file called yts_data.rda. So our data objects or our data files have the extension either .rda in all lowercase or .rdata, the R and the D uppercase. So that will contain, this file will contain the data set, yts, and also this number 5, just x. Okay? So sometimes when you close R, it'll ask if you want to save your workspace. Generally, I don't do that. You can do that, but I don't necessarily rely that something I save to the workspace will be there when I boot R up. That is kind of dependent where you open R. But if you are working with it within RStudio projects, that's not as dangerous. But if you want to save, you want to be explicit about saving something out, saying I did this, or I'm going to stop right here. We ran this long analysis. I want to save this out and maybe open another script and then load this data in. This is one of the ways you can do that. But again, it's not the same way where it's just one RDA or one file contains one data set. That's not the way this works. This can have data sets. It can have, vectors. It can have models. It can have a whole bunch of anything that is an R object, you can save it out. Now, the opposite of saving is loading. So if you have saved this to disk, you can load this into memory. You can, pull it back up. So the ls function is a function that lists things in your workspace. So if you type in ls in RStudio, I'm going to switch that really quickly. So I'm going to go to the environment. Right, if I say x equals 5, y equals 4, z equals 2, you see these values over here. If I say ls, sorry, let's make this bigger. If I say ls, that tells me the things that are in memory, the things that are loaded, the things that I've defined or that are defined. Okay? So like before, we were doing x equals this, y equals that. If you want to say, is x defined? Did I actually, what was it? Did I define x before? You could have just written x right here, and it would say, if you didn't define it, it will give you an error. If you did define it, it will print it out. But if you want to say, what is loaded in memory? That's one way you can do it. Alternatively, you can look at the environment. They should match up. So, one of the ways where you can delete things, clear them out, is the RM command, remove. Okay? So I'm going to say remove. We assign this argument list. I want to take out X and YTS from memory. So I want to clear it out. So clearing is an interesting concept for those coming from Stata. Normally you clear things out of memory, you load in your new data set or something like that. That is fine. You can actually couple these together. You can use RM list equals ls, right? So I'll show you how to do that. And that'll clear everything. So that'll remove everything. That's kind of like a clear. Bless you. So the one thing that's very different between doing this and clearing, for example, in Stata, is that if you have loaded packages previously, so if I loaded package, read R and something like that, library read R, and remove this, I can still use read R functions. And what I'm saying is, when I use RM, that has no effect on what packages are loaded. Okay? Packages and functions are all still available, even if you cleared out, the things you've defined in memory. Okay? So, we listed things out. X and YTS are there. I just defined them, and I save them out to disk. I remove them just to show you that, hey, when I list it again, those are gone. Because when we go to load this, when we go to load that file that we just created, they're now back. Sorry, X and YTS. So I said Z equals load this file. And I loaded it out. Now, you'll also see that Z is now defined. But now note, even though I did this, I want to be clear as to the way you load things in R. Pretty much you don't do this. You don't assign the load to anything. You just say load it, and it opens it up in memory. If we print out Z, if you assign like Z equals loading something up, equals to load this data set, all that will give you back is a character vector that tells you the things that were loaded into memory. Okay? So remember, in that YTS underscore data file, it had X and YTS in there. When we loaded something, it loaded X and YTS. That is what the output was. It wasn't like it actually put the data into Z. That's not what it did. It tells you what was loaded if you assign it. But just doing load, whatever's in this data set, whatever's in this RDA, and it's not a data set, it's our data file, whatever's in here will get loaded into your memory. Okay? So, that's one way of saving things. That saves an RDA file, and can save multiple things in one file. Right? It could be, a table, a data set, a model, some you can technically save a plot in there, stuff like that. And I don't mean the picture of a plot, I mean the code to generate a plot. Okay? If you want to save one specific thing, if you want to save one thing into a file, there's another way you can do that called save RDS. So the way you do that is very similar to save. Just use save RDS versus save. But you can only specify one thing here. Okay? So in this case, I wanted to save the Youth Tobacco Survey data frame to this file. So it's YTS dataset.rds. Okay? So now that's on my computer. And things would be nice if it was load RDS, but it's not. It's read RDS. So I think this is a weird naming convention because either it's read and write or load and save. This kind of doesn't do either of those. It is save RDS and read RDS, right? So it's a little bit, I think, not intuitive, but the big difference here is unlike load, where you just say load the file and everything's in memory, you don't do that with read RDS. You have to assign it out something. So this is different, saying at read RDS, We put the file name in there. Now, whatever was in here, which was that youth tobacco survey data set, it gets assigned to whatever we put on the left-hand side. Okay? And identical is just a function that will return true if things are exactly identical. And all I'm demonstrating here is the YTS data set that we wrote out to disk and read back in, they are exactly the same. Okay? So to summarize really briefly, save and load. Save is good if you want to save multiple things in there. It's a compressed, binary format and stuff, or ASCII format, so it'll save some space. So it's not, it's a little bit more efficient than saving, for example, a CSV, and can save multiple things together. Save RDS is really good. It's good, for project management, but it'll only save one thing at a time. Okay, this way something might seem more intuitive to you. But on the flip side, if you wanted to save 5 or 6 things out, you'd have to have an RDS for every single thing, right? And certain things like, you wouldn't necessarily, this is maybe a choice, but you wouldn't necessarily want to, this is the data set file, this is the model file, this is the table file, right? You might want to just lump them together and use save to have them all in one RDA, right? When you're working in R. Obviously, when you're going to write it up or make tables, that's a totally different thing. Okay, so I put those into the data IO. So if you had downloaded the PDFs or the HTMLs before, sorry, they are updated now. All right, so before we get started, so any questions? So questions about that. I know we covered a lot of technical stuff yesterday. We're going to be touching a lot more on getting your hands dirty with data. We talked about a lot of the point and click stuff in our studio on how to import data, but at the end of the day, you should be copying and pasting that data into, copy and pasting that code into your scripts so that you have it for later. There is a lecture where we touch on this a little bit differently, or a little bit more, but I was going to jump into that because there was some confusion yesterday. So there are 2 functions that are really important with respect to packages. Install that packages. Essentially what that does is it downloads a package to your machine and copies it somewhere on your computer. Okay? That's what install that packages does. Now, the library command loads the functions to the environment so that you can actually use them. So it doesn't matter how many packages are on your machine. If you want to function from a package, you still have to put library. Right? There used to be a page. There used to be something in here that would tell you what packages were loaded. Oh, and it might be in there. So if you go to your options, sorry, I clicked Tools, Global Options. One of your pane layouts can be, I believe, Packages. So you can click one of these, and I'll click it so we can actually see what's there. That might come up by default for you. I don't know why that's coming up. I don't necessarily use that, but that tells you what packages are loaded, if it actually works. But, okay. Now we're actually going to get to some data summarization, working with some data, and really subsetting. So, data cleaning, a lot of it, like a large proportion of it, is really just subsetting data, right? Subsetting data, either subsetting specific columns that we want to, do for analysis to make analytical data sets, subsetting rows that have strange observations, or subsetting rows based on some criteria. So really, this is probably one of the most powerful, tools in data analysis, right? It doesn't really matter, or it matters about what kind of analytical tools, models you use, but if the data is not good, the data is not clean, then it's not very important. And a lot of ways you do the cleaning is by filtering things, based on missing values, based on oddities, based on things that are really outside the norms. If you see someone who's at age 999, you want to be able to identify them, change those values, and replace it. Okay, so again, we use read CSV. That's one way you can get data in there. There are other ways. If you have tab delimited, there's read_TSV for read tab. read Excel. So let's say we have some data in there, and these are the operations we're going to be talking about too. Select specific elements by some index or logical condition. So for example, a logical condition be age is greater than 42, right? An index being like, I want to look at row 5. Renaming columns of a data frame, subsetting rows of a data frame, subsetting columns, adding or removing new columns, ordering the columns, and I mean shifting them around, and ordering the rows. So I'm saying sorting this by, let's say age, all the youngest people are first and the oldest people are last. So these are, for all intents and purposes, 90% what you do with the data set, more or less. Right? We're going to talk about summarization later, where you group things by some criteria, like group it by this treatment group and run this model, or group it by this categorical variable and you run some analysis. That's not what we're talking about here, but with respect to data manipulation and subsetting, this is the large portion of it. So we're going to show you how to do each operation mostly in base R, right? So again, if you just loaded R up, downloaded it from the internet, this would be the way you can do it. It is not very intuitive to new users. We're going to use a package written by Hadley Wickham called dplyr, which allows a lot more intuitive ways to manipulate data sets. One of the big reasons, again, why we're going to show you base R is that's how a lot of answers are going to be given to you. So there's a lot of resources on dplyr that exist. Jenny Bryan has a really good introduction, Stat 545, to dplyr. It interfaces really well with data frames. And again, data frames you can think of just as a rectangular spreadsheet, more or less. That's what we're going to be working with. Tibbles are data frames. They just have some other nice properties, like when you print them out, it doesn't print thousands of rows. It only prints the first 10. It doesn't print all the columns. It only prints as much as kind of you can see on the screen. Okay, so data frames, that's what we'll be working with. So before we get up in it, that's what we're working with for the day today. Before we go into data frames, we should talk about subsetting in general. And so we showed this a little bit yesterday, where we changed the column names. The first column name to be all caps year to be lower caps year. One of those examples. So the way you do subsetting with vectors is this bracket notation. Okay? So x we just define as a vector of length 5, 1, 2, 1, 4, 2, 8, and 10. And let's say I want the second element of x. I say x, square bracket, 2, and square bracket. Get the second element, we get the number 4. Right? If I want the fifth element, we just put 5 in there. But square brackets are the way you do subsetting for vectors. And again, this is subsetting by index. We are going to get to how you subset this based on some condition that's like x is greater than 5. So if we want the fifth, we should still use bracket. But again, if we want to do multiple indices, right? We want to subset on the second and the fifth element. We have to group them together into a vector inside the brackets. So I want the second and the fifth element. I need to see around these things. If I don't do it that way, it means something completely different, or it won't give me an answer at all. So this is a vector, and we're passing in a vector of indices. Does that make sense? Might not be so intuitive, but at least that's what we're doing. So negative subsets do exist. You can do them. And what that does is instead of grabbing that element, it gives you that vector back, deleting that element. Okay? So if I say x negative 2, that means give me x back, every single element but the second one. Okay? So sorry, I think we switched those around. So this is 1, 2, 4, 8, and 10. 2 is the second element. I said take that one out. It removed it and gave me everything back. So for example, if you're working with a data set and you say these are the indices with bad rows, right? These are the bad cases. I don't want to include my analysis. You could use a negative index to remove them. So you have to be careful when you're dropping with more than one element. So again, x, square bracket, we're doing subsetting. We're grouping these together, 1, 2, 3. But when we put a negative out in front, it negates each one of them. So if I do negative C, 1, 2, 3, what's it going to give me? Negative 1, negative 2, negative 3. Okay? So what this will do is it'll drop the first, drop the second, and drop the third element. Note, we didn't talk 100, so we've breached on this a little bit. Colon again means give me a sequence from the left-hand side to the right-hand side. 1 colon 3 means 1, 2, 3. 1 colon 100, 1 to 100 by 1. So if I do this up here, x bracket negative 1 colon 3, that's going to give me a sequence negative 1, 0, 1, 2, 3. Okay? So this means something different than this. Remember, the parentheses are an operation like addition and subtraction and all that other stuff. So when we do these parentheses and then the negative, it's like we multiplied everything by negative 1. It respects the order of operation. This just says, give me a sequence from negative 1 to 3. This says, give me a sequence from 1 to 3, and then make the negative of all of them. Okay? So this will drop out again. So these are exactly equivalent. This, you could put any vector in there. Any vector of indices. 1, the 5th, the 2nd, the 3rd. The colon just says, oh, I just want a sequence from 1 to 3.
Would it work if you said like x minus 3 to minus 1?
So it'll do that. Oh, so if you, yes, I get what you mean. So yes, it doesn't, the order of the indices doesn't matter. And they can be repeated. So let's demonstrate that. So let's say x is this. And you want to say, let's drop the 3rd, the 2nd, and the 1st. Give you exactly the same thing. This, on the other hand, doesn't work. Because again, negative 1 to 3 is going to give us the sequence. So you can't put, so only zeros may be mixed with negative subscripts. So you can't have negative and, you can have negative and positive, I believe. I don't think actually you can have negative and positive. Maybe I'm wrong. Yeah. You can't have negative and positive in there, right? Because this means drop everything but this, and then you're saying grab the 3rd element. So that's not really that clear to R. But, that being said, they don't have to be unique. If you said, I want the 3rd element 3 times, you can do this, right? It doesn't matter. It'll just repeat, right? It says it doesn't know, like, it doesn't care that you want a repeated element. It just says, grab me the 3rd element, grab me the 3rd element, grab me the 3rd element, grab me the 4th and 5th. Okay? So, like, let's say x is, again, I'm going to be using age a lot because it's an easy numeric thing to think about. But let's say x is a vector of ages, and I want to only know, do a histogram based on some subsetting of that. So most of the time, though, a lot of times you're not subsetting by index. You're subsetting by some sort of logical condition, okay? So here's your first logical operator, the greater than symbol, okay? So here's x, 1, 2, 4, 8, and 10. If I say x greater than 2, it returns trues and falses, okay? So like before, we had numeric types, we had character types. Here we have logical types, okay? So when I say x greater than 2, it comes up true for those that are greater than 2, false otherwise. And we can put that logical vector into subset x, right? So here we say, give me the elements of x where x is greater than 2. So in brackets, you can put index, 1, 2, 5, 7, 10, or whatever, or you can put a logical vector, right? And that'll grab those ones that you want. So for example, give me the ages where the age is greater than, 26 or something like that. You would say age greater than 26. And then maybe you want to do a histogram of those. Because let's say you did a histogram of age, and there was some very interesting stuff in the tails, but there were so many ages it was hard to really explore, and you wanted to only look at the ages greater than 26. Yes?
When you did the x bracket, x greater than 2, does that redefine x as only the ones greater than 2, or is it just exploring the data?
Only exploring the data. X only gets redefined when you say x equals something. Good question. So again, if there's no assignment, nothing gets changed. This is a great point, because in other systems, you say sort, you say order, you say whatever, it does it to that thing. That is not the case. That will only happen if you reassign it. So say x equals sort x. Then it'll give you the sorted x, for example, in order. But unless you do that, unless you reassign it, nothing happens to it, just subsetting and looking at the data. All right. So there are the things you would expect: greater than or equal to, but they're less than or equal to. But there's also logical different logical operators. So greater than, less than, they're called comparison operators because they compare things, and or are logical operators because they work on logic. The symbol for and in R is the ampersand. The symbol for or in R is the pipe. So it should be below or above your enter button on your keyboard, I believe. It's just a vertical line. Usually you have to hit shift to get it. So we don't have to just put one statement here. We can make compound statements, anything like that. They will follow the rules of logic. And I mean that in the sense you have to group things together with parentheses that you want to, you want that condition to work together, let's say. So here, I don't want just x greater than 2. I want x is greater than 2 and x is greater than 5. This statement within the brackets will give me a logical vector back of trues and falses where that condition is true. In this case, in that vector, the only element that satisfies that condition is the number 4. So here, we want to say, I want if x is greater than 5 or x is equal to 2. So that gives us 2, because we said x is equal to 2, and anything greater than 5. Now, big thing, double equals. Double equals is the comparison operator in R. Okay? You want to say, is something equal to something else? You have to put 2 equal signs. That's how you test it. Okay? If you said, so if you don't put double equals, R will say something like this. Unexpected equal sign in that. So the way R sees things, that equals and that double equals are totally different things. Okay? So although to you it's just another equal sign, to R it's a totally different thing going on behind the scenes. Give me 1 second. Okay. Really quickly. So the other operator, not equal to, is either the exclamation point equals or some call it the bang equals. I've actually read that like many times that people have called it the bang, but I've never heard a single person ever call it that. So probably just like years ago, it was like, we'll call it the bang, and then no one did. So tilde equals in some of the languages works, doesn't work here. Got to use the exclamation point. If you broke the exclamation point on your computer, you're not going to be doing not very much. All right. So again, I wanted to show you x not equal to 2 will gives us trues and falses back, just like x is greater than 5. So it'll give us logical things, trues and falses. Note, they don't have quotes around them, right? They're not characters. They're a different thing. They're letters, but they're not interpreted as words to R. So if you want to take that logical vector of trues and falses and all that kind of stuff and get the index, or the indices for where it is true, that function is called which. So we pass x is greater than 5 or x is equal to 2. We say which, and it'll tell us the second element, the fourth element, the fifth element. Gives us that. Okay? Not the, it won't give us the values of x, right? It just tells us the indices. But if we want, again, those values of x, we can still pass this in here. We take these indices, put it in the brackets. So, I think to new users, this is something we've demonstrated a little bit here and there, but it's a little confusing. It's a little bit off the walls starting out. So, pretty much R evaluates things from the middle out. So, it sees you're doing brackets, right? It sees you're subsetting, but then it also sees you're calling this function which with this logical vector. So what will happen is it'll say x is greater than 5 or x is equal to 2, give you a true or false back. Then it'll evaluate which, give you the values 2, 4, and 5 back. Then it'll do the subsetting and say give me the second, the fourth, and the fifth element of x, which you get 2, 8, and 10. Okay? So it's confusing, I think, because you're doing subsetting, but you're passing in a function. But what's happening in R, it's evaluating that function. It gives you a vector back, 2, 4, 5, and more or less puts it in there for you and subsets. So, and I just want to demonstrate using which and using this. For this case, they're exactly equivalent. It just tells you which ones are true and gives you the same things. There are some reasons to use which versus a logical vector, but for the most part, I do most all my subsetting like this. There are some speed requirements. There's like some efficiency things that if you have really, really, really big data sets, this can be more helpful than computing this. Okay, so I'm going to discuss really quickly tibbles versus data frames. So there are some data sets that are toy examples that we're going to use, and those are preloaded in R. Empty cars is one of them. So if you just go into R and you say empty cars, what happens? If you try it out, you should get a data set. Right? These are a bunch of vehicles with their miles per gallon, number of cylinders, horsepower, weight, all that kind of stuff. Cost. All right, so empty cars is something that's already in there. If it's a data set, you can also, a little different, you can say data empty cars just to make sure that it is loaded. So what we're going to do is make a copy of it. df is equal to empty cars. Again, df, same thing. Printed it out, miles per gallon. Note, you don't see a header over here. That is because this data set, for some reason, they like to encode their data in the row names. So if you output this as a CSV, you definitely want the row names in there, otherwise you're not going to know which car it is. That is a bad strategy. That is bad behavior. That is not good because you want any data that's relevant to be defined in a column of your data set. And that is not a column of your data set. It's just an attribute. So if I run this, I get an error. It says, I don't know what you're trying to do. I don't know where that function is. That's because it's in the dplyr package. Okay, so two things. Everyone, go to install.packages. Let's go tools, install.packages, dplyr. Okay? I'm not 100% sure if it was already, so it could have already been downloaded with readr. I'm not 100% sure, but we're going to install it again anyway. Click enter. So sometimes you will get this warning. Hey, you have this package loaded. I just loaded that package into my R session. And it says you're going to reinstall it. You're going to overwrite the package that's on your hard drive. What's going on? Are you sure you want to do that? Most of the time, it's fine. Sometimes you want to restart your R session. So it's saying, I'm going to restart your R session. I'm going to do the installation. You say you want to compile. The answer is yes. This might take a while, so I'm going to let that run. So you're going to download and install dplyr. So dplyr is the package that has some of these more intuitive ways to manipulate your data. So this might take a while, or not a while, like a minute or two. And what we're going to do is demonstrate the difference between tables and data frames. But in the meantime, while that's running, I'm going to kind of move on a little bit. So we'll talk about the difference between a table, or tibble, TBL, and a data frame. Again, for the most part, there are 2 to 3 big aspects that are different. One is printing. It will not print every single row of every single thing from that data set if you accidentally print it to the screen, which is helpful. And I mean, it won't print every row. It also won't print every column. Yesterday, we demonstrated a little bit that under the header columns, it will describe what type of data that is, whether it's an integer, a date, whether it's a character or something like that. And the third thing that's really important, which we're not going to touch on today, it allows you to assign groups to that data set. So let's say you have a multi-site data set, right? Or I think somebody was talking about the DHS yesterday, which has multiple countries, right? So let's say you want to do some operation by country. You can group that data set by country, and then when you perform operations, it'll do that operation, but it'll do it separately for each country, which is something that you usually want to do. Almost undoubtedly, in almost every analysis, you do some sort of subgroup analysis or stratified analyses, and that grouping is available in a tibble, but not in a standard data frame. That's why they kind of created these things. But for all intents and purposes, you don't have to know the specific details of what they do. Just when you group a data set, it might look different when you print it out than if you read it straight in. If you read it straight in and it becomes a data frame, when you do the grouping, it converts to this other object that prints nicely, does some grouping, and that's what you need to know. But sometimes it can be a bit confusing when you read something in, print it out, do an operation, print it out, and it just looks different. The data has not changed whatsoever, but it might look different, and that's why we were explaining these. Because the output of almost every dplyr command is a tibble. Okay, so great. Now I copied over empty cars. I have to load the package in, right? So library dplyr. Okay. We'll talk about what that means in a second, but I'm going to say tibble, and then I'm going to say df. And I want you to note
Can you make it easier for us to see your script?
my script.
Or I guess you're not doing it.
So I'm just using, all I'm doing is the things in the lectures, just these 3 commands. Sorry, yeah, okay. So all I did was df equals empty cars. Tibble is as.tibble df after I loaded in the dplyr package. So it should be on the left-hand side. Okay. So if I say tibble, it'll print out the first 10 rows. It'll say it's a tibble with 32 rows, 11 columns. It says the miles per gallon, cylinders, all that fun stuff. Double. These are doubles, right? So it's just saying it's a numeric thing. That's the way it prints. Now if we look at df, right, and it says, I did not print these other rows. I stopped at 10 rows. There's other rows in there. And I stopped at these columns because your screen wasn't that big. I don't think you want me to flood your screen with information. If I say df, and I print it out, It'll print every single row and every single column. It won't tell us what data types each things are. But there is one more very important point. Tibbles don't have row names. So remember I click, so here in the data frame, I know that this row is the Lotus Europa. But if I look at the tibble, nothing's there. It's 1, 2, 3, 4, 5, 6, 7, 8, 9. So, sorry, I'm trying to get this out of the way. So, what I'm saying is, if you're using tibbles, make sure your row names aren't important. Okay? So sometimes, at least if someone gives you data sets or RDAs where that is the case, we will show you how to say, change the row names. So row names, like column names, I'm going to pull that up. Row names, like column names, is a data set that gets one of the attributes, either the row names or the column names. And we're going to show you later how to assign this to a column of the data set. So you do actually know which car it is. All right. Now, we showed you this briefly yesterday, and this should make a bit more sense. So before, we took the column names of the data set, and we subset them to the first three. So the column names of data frame, remember our miles per gallon, cylinder, all that kind of stuff, 1 to 3, are equal to MPG, CYL, and DISP. All caps. So all we did was make them capitalized. All right, so when we print it out, so again, we use head just to show the first 6 rows to kind of get a gist of what's going on. Now we see that the first three columns have been renamed. So that is one way to rename the columns of a data set. This is good, but if for some reason your data set got reordered and the first 3 columns weren't those first 3 columns, that's not the most robust way to code that. So, but that's one way you can rename columns with the column names function and assignment. Okay? Here, you could have done it where you say column names df, you don't have to put any subsetting, and you could have put, all the, a whole vector with as many names as there are columns, and renamed all the columns at once if you'd like. But again, they have to be in the exact order in which the data set is in. Right? So it's mile per gallon, cylinder, just HP, drat, all that kind of stuff. So if you were going to give a vector, it'd have to have, whatever the second one you named, whatever the second one in your vector would correspond to the second column of the data set. So this, all we're doing is resetting the back for consistency in the slides later. This is not important. But again, same operation, we're just setting the back. So now we can combine some of the things we've done before. So column names is kind of a two-sided function, I'll call it. You can use it on the left-hand side when you're assigning column names. You can use it on the right-hand side when you're trying to grab the column names and assign it to something else. So CN, I'm going to say CN is equal to the column names of DF. So MPG, CYL, DISP, HP, TRAT, all that kind of stuff. All right, so I'm going to do this really quickly just to demonstrate what I'm talking about. Oop. Just gives me a vector of all the names of the columns. Okay? And again, you should be able to grab the R from the website. If you want to follow along from the website, there should be the R file associated that has all the code in here. So now we combine the two things we've been talking about so far. We subset. We're going to say CN is equal to DRAT, right? Find which one that is, and then assign that to this capitalized version. Okay? So now all the column names are exactly the same except for the one that is equal to DRAT. Right? Everything's exactly the same except for that one. So we said, I only want to rename that one. And then, now, like I said, it's kind of a double-sided function. Column names on the left-hand side now says take a vector of column names and assign it, or take a vector, on the right-hand side, and assign it to the column names of the data set. So now if we look at the data set again, all the columns are exactly the same, except the column name for DRAT is different. Okay? And again, I'm just going to reset it down here. But again, we didn't have to do this 3-step process. We could do it in one long statement, but sometimes that's not that clear to code. So here, it's clear that we assigned CN to the column names, we changed one of the values, and then we assigned it back. Here, we grabbed the column names, subset it, called the column names again, said which one is equal to drat, and assigned it to the lowercase version. That, to me, is fine, but sometimes it's not as intuitive. It's not as straightforward. It's a little bit more convoluted. It's a little bit more complex to read. That's all. All right. So now, load it up. So sometimes it says objects are masked. So let me scroll back up when we load it in dplyr. It's going to say some stuff, of course. Yep.
The number 2, STBL, is that something we have to look separately?
Excuse me, as.tbl. So this is a function in dplyr. So you have to load dplyr using the library command before you're allowed to use this function. Does that make sense?
Yeah, I loaded dplyr, but that didn't work.
As.tbl.
How can we be sure the dplyr actually loaded?
So,
I wasn't sure.
well, you'll see this for one. You'll see this big thing that says things are
see some stuff, but I don't know if it was the same thing. But
so usually you put it like up at the top of your script, and a lot of packages load, but they don't have this kind of printout. But it should be loaded in your memory. But okay, this is a good point. You can there are a few instances where the order in which you load packages is important. But if a package is loaded, running the library command is totally fine. You can run that as many. So like, it's just gonna say, if I say library dplyr again, nothing happens. Because if you do the library command again, it's gonna say, if it's not loaded, load it. If it's already loaded, pretty much don't do anything. So you can run this again, and there's gonna be no harm to that. So some of these things, it says the following objects are masked from package stats. Like I was saying before, you can have, Leslie, do you want to see if like why as.tbl doesn't work on hers?
Yeah.
So, like I was saying, you can have hundreds of packages on your machine, and a bunch of them can have functions of the same name, right? So sometimes it says, so when you see this, what it means is that in the stats package, there are functions called filter and lag, okay? dplyr also has functions filter and lag. So it says you had the stats package loaded up, you called this package on top of it, and so when you go to run filter or lag, it's going to use the dplyr versions. Now, we will talk a little bit later how, if you really want the other versions, you can do that explicitly. But, so if I say filter, and if I just print this out, doesn't necessarily matter what the function definition is. If you just put the function without parentheses, it shows you the function definition. Don't worry about this. The only thing that's really important is namespace dplyr. So you know when you print this out, if it'll tell you which package it's calling it from. So when we write this, it says this is the filter function from the dplyr package. Because when it says mask, this function from the stats package is totally different. It doesn't do anything remotely the same. They both thought filter was a great name, so they both went with it, and that's kind of how it is. So that's what I'm saying. So filter in dplyr is for subsetting rows. Filter in the stats package is for like temporal filters and stuff.
Sorry, just waiting back. When I tried the CN, the call names command attaching it to a variable, it didn't actually change my.
No. So this on the left-hand side doesn't do anything to the data set. So these are not linked in any way. So when you say column names equals this, CN is just something you have in memory.
You have to reattach to the.
Yep. So this vector Cn is in no way, shape, or form bound to that data frame anymore. Okay? So once I did this, I could do this, for example, Cn. And then Cn equals 5. Doesn't matter. After you do this command, Cn is on its own. It's something completely separated from the data set. Only when you say column names df equals some vector is when it's reassigned, when it changed. There will be a way we do that where it's a little bit more intuitive. There is a rename function, but sometimes it's a little bit easier to do it this way when you want to do renaming of many, many, many columns, for example. Like, for example, if you want to get them all to lowercase, stuff like that. All right. So the way you can call, and I did this a little bit in the data I/O lecture. I used these 2 colons for some reason. When you say package : function, that is being very, very explicit, saying I want this function from this package. Okay. So when I say stats : filter, that will call the filter function from the stats package. If I had a dplyr : filter, that code, I know 100% of the time it will call the one from dplyr, no matter what other packages are loaded. Okay? So sometimes you'll see this more and more in code. So package : function. And this will allow you to use those functions that are masked. So it said, when you load a dplyr, filter, lag, all these other things are masked from this package. Which means if you want to use them, you have to use this syntax. So all I'm noting here is I'm just looking at the first 2 lines of the function. It's a completely different function than the one before. It doesn't do anything remotely close to the same thing. The reason that's important is if you call this on a data frame, on a data set, it most likely will error, or 2, it might do something that you don't intend it to do. You want to use the dplyr. Okay. So again, this is a little technical stuff, but that's what that warning or that message means when you load up the dplyr package. Is that you had other functions loaded from other packages potentially, and now if you're going to call these specific functions we listed out, it's going to use the dplyr versions. Okay. Now, more intuitive stuff. So that column names, Cn equals column names, and so forth, that is the base, that is the way a lot of people who've worked in R many, many years, that's how they rename things. So there is a function called rename in the dplyr package. So if I say dplyr : rename, I pass in the data set, and then I say, what is the new column name equals the old column name. So I want to make MPG in caps, right? I want to say rename lowercase mpg to uppercase mpg. Now, if I didn't put this back here, if I didn't put this df equals, nothing will happen to the data set. It will just print out the output. That is it. So if I just do this, yep. Let me see. Sorry, I didn't do this. Sorry. Again, it just, sorry, I want to demonstrate when I run this. All it does is it prints out a data set. It didn't reassign it anywhere. It didn't do anything. I'm going to scroll up and show you the column names and show you that MPG is now changed. But if I print DF now, and I'm going to use head so we don't print out every single column. The first column name is still lowercase mpg. Nothing happened to that data set until I reassigned it. Okay? So df is equal to this renamed data set. Okay? So again, syntax is rename, data frame, new name equals old name. All right? So I just reset it back because we're usually going to rename some of that more and more. So one, the rename function from dplyr allows you to rename columns. One thing to be said it's a bit more explicit, right? It does some more checking. So it's a little bit more, work to, if you have 1,000 column names, maybe this isn't the way you want to go. That's why we still show you the base way. Because if you want to make every single column name lowercase, that's really simple with the base way because you're just manipulating a character vector. Cn is just characters. We know how to make them lowercase very easily. There's a function to lower, T-O-L-O-V-R. Right? Yes?
Double colons, do you need that whenever you have two functions with the same name? I thought that you only use it for the masked one. Like I was just,
Yes. So
and
that
dplyr is not masked, right?
dplyr is not masked,
Okay.
and actually it wasn't in that list. It wasn't in that list of masked functions. So so we wouldn't have to use that regardless. So there is no other rename function floating out there. But if you just but if you did load another package after dplyr that had a rename function, then you can use this. But I'm saying even if it's not masked, this syntax still works. Okay? But yes, but we don't need this after we loaded dplyr if it wasn't one of the masked ones.
So you can use rename without the double.
Exactly. So if I just go rename, I'm gonna oops, sorry about that. Do the head. First column will be capitalized MPG. I didn't have to use the double colon. I could just use the rename function. Generally, this isn't a big problem, this masking thing. But if you have 15 packages loaded, unless you and a lot of times, even if you have multiple packages loaded, which is not uncommon, many times you're not trying to use, there's not that many conflicts. There's not that many times where they name things the exact same thing. So it's not usually that big of a problem. Okay, rename function, renames columns. Subsetting columns. So if you have a data frame or a tibble or whatever, the way you can subset a column name is with the $sign. So if you define an object in R, if you name something, you cannot have a $sign in the name. So df $sign means take this data set, $sign, grab a column, and the column is carb. Okay? If we grab that, what it's going to give us is a vector back. The number, I forget what that column name is entailing. But it gives us a vector back from that. So it peels off a column. Right? This is no longer a data frame. This is a vector. Okay? $signs give vectors back. But you can only grab one at a time this way. $signs grab one column. So, like vectors, you can subset with brackets. But the notation is different. Because you don't just have one dimension anymore. You have multiple. So the way you do it is the same way, is the way you subset is bracket, row indices or row subsetting, comma, column indices or column subsets. So it's row, comma, column. Okay? So for example, and if you don't put anything in there, in row or column, df nothing, comma 11, it says pick off the 11th column of that data set. Okay? So this is one way. So data frames, there's another. So there's two-dimensional classes, matrices, which are two-dimensional vectors. But again, but matrices all have to be the same class. So if they're all logicals, they have to be all logicals. Or characters, they have to be all characters. Or numerics. Data frames, again, are different. They can have different data types and different columns. So, but, sorry. I don't know. Oh, that was, okay. So if we want to grab the 11th column, that's one way we can do it. But again, what if the 11th column changed? Somebody gave our data set in a different way. We didn't know that we wanted the 11th column, but we knew we wanted the carb column. We can do it this way. df, all the rows, comma, the carb column. Okay? So that is two ways you can pick off one column. So, sorry, let me go back really quickly. We can put a whole character vector in here. We don't just have to put one value. We can put carb, MPG, all that kind of stuff. As long as we collect them together with the C function, we can put them here. Okay? So there's a little bit of a difference when you're doing bracket subsetting. The dollar subsetting works for everything that's a data set, more or less. Data set, $, column name, it'll give you the vector of those values. Brackets are a little bit different. df bracket 1, when df is a data frame, gives you this vector. When it's a tibble, bracket, comma 1, returns back a tibble. Okay? This has one dimension. It's a vector. This has two dimensions. It just so happens the number of columns is just 1. Okay? That is important because some functions say, you didn't pass in a vector, I don't know what you want to do. You want to do a histogram, pass me in a vector, we're all good. If you pass it in something that's not a vector, it's not always so happy. So the output of these two operations is different. Again, we will not really show you, this is important because sometimes you may do this operation, it gives you different things back, so you have to know kind of what type of output. You can always do class on this, it'll say this is a tibble, class on this, it'll say it's a numeric, so that you know what's coming out. But they just have different behavior. So data frames are great. They are described as like the Cadillac of data types or data classes in R. Tibbles expanded on that so that there was a bit more consistency and a bit better printing. Because a lot of times when you do this, sorry, going back to this, maybe you did want to grab just the first column. But maybe sometimes your code, the way you got this 1, maybe it would give you 1 and 2 back. Okay? Maybe it's subset of 2 columns. Like your code says, give me the columns that match this criteria first. And in this case, it was only 1 of them. It gave you a vector. But many times when you do this, you don't want it to just grab that column. You want it to keep the row column structure. That consistency is here. So it does the things, it returns the same type of object after doing a subsetting operation. There's a tibble, you subset, you get a tibble. Data frame, you subset. If it was 2 columns, you get a data frame. If it was 1 column, you get a vector. Inconsistent, more consistent. Again, all right. So it might seem like we're down in the weeds, but this is where some of the errors occur when, you say, I did this, it just worked. I did it this way, it doesn't work. And it's because of some of these behaviors. So that's why we're talking about these 2 types of classes. So again, to subset multiple columns using base, you can say data frame, bracket, all the rows. We didn't subset any of the rows. Multiple columns, MPG and cycles. Gives us those columns back. We could put all the columns there. We could put, I think you can repeat them. But if you want to subset a set of the columns, that's one way you can do it. So, select is the dplyr way. So rename is in dplyr. It renames column names. Select selects columns. It subsets columns. So the one big difference in here, you have to put the column names around quotes. It expects a character vector. It expects you to subset things based on either index or a character. Here, you don't have to do that. You say select dataset, column name. Okay? And then you'd separate these by commas. So if I want the cycle and the miles per gallon, that's how you do it. Okay? So select grabs columns. All right. So let's go back really quickly. So we showed you some of the subsetting like this. That is the way base R does it. Again, because if you get any code from an R programmer or someone else, they're going to do a lot are going to do stuff this way, and some of the help will. This $sign though will work for either one. So if you say I just want this column, I want it to just come back as a vector, you use dataset $sign column name. It's all good. Select is a more intuitive way. It grabs the miles per gallon, it grabs the cylinders, and it gives you back a data frame with the correct information. Now also, note, I selected two things. We got rows, we got columns. I selected one thing. It still gives me back rows and columns. Okay? Okay. So, subsetting rows, for the most part, is very, very, very similar. Except where you kind of put things. So before, we said the bracket notation, it's row subsets, comma, column subsets. So this means I want the first and third rows, and I want all the columns. And that's what we get back. Okay? So where that comma is means a lot. If you put stuff, then a comma, that means I'm subsetting rows. If you put a comma, then subset indicators, that means columns. Okay? A lot of times what you want to do, usually you subset columns by name, right, by a character vector. A lot of times you subset rows based on some sort of logical vector. Right? Data frame. I want where the data frame miles per gallon. So again, we're going to grab this column. It's greater than 20 or it's less than 14. Right? So I want, kind of the disparate ends of miles per gallon, and then it gives us that data set back. Nope. It doesn't resort it or anything like that. It gives us back, it just says trues and falses, gives us things back in the order in which they were, just deleting the rows where this was false. Okay? So again, logical vector, comma, all the columns. So just like in vectors, you can subset based on logicals, or you could again indices here. And again, you can combine these two where I want to say it's less than 14, it's greater than 20, but I want only these two columns. Okay? Yeah.
Can you create a condition that says, for instance, I want all of the values in the MPG column that are equals to 5, 10, 15, and several values?
Yes. You don't use the equal sign for that. We'll talk about that. It's called percent in percent, where you give something on the left-hand side, you actually put percent, the word in percent, and then you give a whole list. And it'll give you true if the thing on the left-hand side is in the list on the right-hand side. We'll get to that. So just to be clear, you don't have to do x is equal to 2, or x is equal to 5, or x is equal to 6, over and over and over again. So those who use Stata, if you've ever used the inList function. Right? All right. Base way, dplyr way. You say filters rows, subsets rows, select subsets columns. So any of those who use SQL, this will make a lot of sense. So filter, you put in the data set, and then you put in the criteria. MPG is greater than 20, or MPG is less than 14. You don't have to use the $signs. You don't have to use, DF $sign like we did here. You can just say MPG, and it knows that this is a column of this. That MPG is a column of DF. Even though in other functions in R, these are special functions. These functions understand that this means a column of the data set. Whereas other functions in R are not, let's say, are not built that way. And if you put this in there, it would say, hey, I'm going to look in the environment for MPG. I'm going to look for something if you defined a variable called MPG. And I mean an object, not a variable in a data set. Here, it understands that these are columns in this data set. Okay. So, filter, if you put in multiple conditions, it joins them by and. So, filter data frame miles per gallon is greater than 20 and 4 cylinders. Right? That's the condition we want. We could have written it this way, explicitly with the and. We could have just put MPG is greater than 20, comma, sil equals to 4. Bring it up. Right, I'm saying, so this is the command. This is the same exact command, but if you put a condition, comma, a condition, it says this and this and this, right? So it's an intersection of all these. But if you want to use or, you have to be explicit about that. You have to be explicit and write this. You have to use the logical operator if you want ors. Filter assumes you're doing ands. Now,
but in case you put it, it doesn't matter. Right? It's a filter assumes you are doing an and.
yes.
But
If you just put comma, if you just put condition, comma, condition, comma, condition.
If you happen to put a ampersand sign,
Yes.
it doesn't matter.
It'll do the exact same behavior, right? It's just when you're using or, it's different. Right? If you and, totally fine. But sometimes you might want to do and, this or that. You have to be explicit about that. So this has to return a logic, like a logical thing. It's a logical test. So filter based on this logical condition. Oh, where did I go? So you can combine these. So again, R works from the middle out. So what this will do, filter data frame. Grab the miles per gallon that's greater than 20, and when they're 4 cylinders, what it'll do is it'll give back that data set, right? So this is the first argument into select. So this right here doesn't do anything to the data set, but it will return a data frame where we only this condition is met. And then we wrap that whole thing in a select and cylinder and horsepower. So what we did was, these are the cylinders and horsepowers of, cars with a 4-cylinder engine and greater than 20 miles per gallon. Okay? So you can start combining these. And we're going to show you a more intuitive way to write these in like a sequence. But note, let me see, did I reverse it? So, if I reverse the order of the operations, this will not work. Okay. And I mean, let me put this down here. So by the way, white space doesn't matter in R. If I run this, I'm going to get an error. MPG not found. That's because this operation only selects these 2 columns. So the only 2 columns coming back in this operation are cylinder and horsepower. But when you start saying, well, let's filter it on miles per gallon, that variable, that column's gone, right? So the operations can be order dependent, especially if you're dropping a variable that you want to subset. Right? So does it make sense why this doesn't work? Right? So we removed miles per gallon because we only selected these 2 columns, and we wanted to try to subset it on it later, and R said, I don't know what you're doing. I don't know where that variable is. Okay. You can do, so a couple years ago, this would be the recommended way. So let's say df2, let's filter that, and then let's select the rows. So do it in 2 steps versus this huge nested thing. Okay? So again, same exact operation. Filter the rows, miles per gallon is greater than 20, and 4-cylinder engines. And then we put this df2 in here, and then let's grab those two columns. Same exact operation. So in recent years, so let me step back. I think this is fine. If you think this way, if this makes the most sense to you, just reassigning over and over again, fine. That's the way I used to do. I've done it for years. The newer way is called piping. So what you do is you take an object, in this case a data set, and you pipe it into a function. So the same exact operation we were just talking about. You say data frame, I want to pipe it into the filter function. It says, okay, take this data set, filter the rows, same thing we did before. Now that resulting data set, remember, it only has the subset of rows we care about, pipe that into the selector and grab only the columns we want. So the pipe is this percent greater than percent sign. And if you hit Command-Shift-M or Control-Shift-M in RStudio, it'll give you that operator. But in essence, this operation, and this operation are exactly the same. The only big difference is readability and being able to read the code and understand what's going on. To many people, to a lot of new users, this makes a lot of sense, and this is the way it's been adopted. So you take a data set, you put it into a filter command, and then you put it into a select command. So you don't have multiple lines where you keep reassigning. You would just do one reassignment, and then you would chain these together. All right, before we go on, does this make sense? Because we're going to do a lot of code like this, where we pipe things in. So the left-hand side is piped into the right-hand side. Whatever happens there is then piped into the right-hand side. Yes?
And you said the alternative was to do the two functions, like one after the other?
That is one alternative way. So the only difference between this and the last one is I didn't want to overwrite df in this case. So I wrote it to df2, and then I selected it, and then I overwrote df2. So that's one way, and I think this is a lot more readable than this, right? So this is probably clearly the least readable code, and it's not as intuitive what's going on because the middle out structure, right? It does this, then it does that. This is more intuitive to read, and it's clearer to see what's going on, but you have to do reassignment. This is probably as clear, and you would only have to do one reassignment on the left-hand side. Okay. Adding and removing columns. So the dollar sign operator will grab columns from a data set, but you can also use it on the left-hand side to assign new columns. So let's say I want a new column on df, and I want it to be equal to the weight column divided by 2.2. Okay? I say, make a new column. It's equal to this. So now we see in our data set, we have a new column. So if we just did, so again, this is grabbing a column, dividing it by 2.2, assigning it to something new to this data set using this dollar sign. And we note that it exists, it's there. So the dollar sign is one way you can do it. One way you can remove a column. We will show you how to do it with select, but there's a specific type called null. So if you say df column name equals null, it'll remove that. So again, just to be clear, whatever your data set's named, sub that in for df. I'm just using df over and over again because we assign that to something, right? And we use df to make it clear that that is the data frame object versus the tibble object. That's all. That being said, I do use df a lot as like a data frame object, or dat. So df, so we remove that column. It's no longer there. Right? So if we had looked at it, that would be no longer there after doing this operation. Yes?
So what does that 3 refer to in this case?
Sorry, what does what refer to?
In the command
I only wanted to print 3 rows. So I just didn't want to print out all 6, just because I didn't need to look at all 6 of them to show that the column was deleted. That's a good question. So there's 2 arguments to this function, whatever you want to put in and how many rows you want to show. The default 6 for some reason. So again, we could have just subsetted rows a similar way like we used with column names before. df bracket, again, all the rows, column names df doesn't equal new column. So that this operation will give us trues and falses, and it'll be true if the column name isn't new column. So this is another way to delete columns. And similarly, if you wanted to have like a whole bunch of things, a whole bunch of column names that you wanted to drop, there's a way to do that with the percent and percent operator as well. Instead of doing this or that, actually column names doesn't equal this and column names doesn't equal that, and so on. All right, 2 ways. If you want to assign a single one, $ equals null, or you can use the bracket notation. To add to a data frame, to add another row, there's also another way, except, before we said df $ new col equals this. One way you can do that is C bind for column bind. So bind a new column to this data set. So bind the data frame, new col equals to this. So, that is unfortunate because it doesn't show you new col. It's down here. So new col's in there, trust me. Right? If you run that command, I'm gonna run it. New col's there, great. Right? Again, nothing was done to df, even though you say cbind, nothing's actually done to the data set until you reassign it. Okay, mutate. Filters rows, selects columns. Mutate adds or changes the data. It mutates it into something different. That is one way you can create a new column. df, I'm going to reassign it, is equal to mutate the data set. New col is equal to weight divided by 2.2. Don't worry about the print. That is just so it prints out. That's all. So mutate, we put new column name is equal to, we can use whatever columns are in there. If new col already existed, it would overwrite it. Okay? So it doesn't say, hey, like in Stata, gen new variable. You already have one of those variables. Doesn't care. It overwrites it. Okay? One way you can drop columns. So mutate, mutate adds new things. Select, you can drop them with the negative sign. Right? So select, before we said miles per gallon, that kind of stuff. We listed out the ones we want to keep. You can say negative column name if you want to drop it. Okay, so this is every column but new column. So select is for subsetting, that being said, keeping or dropping columns. Keeping specific ones or dropping specific ones. I will still say the null method is still very common. Just if you want to get rid of a column, df $ new col equals null. That's still done very, very commonly. dplyr also has a lot of these other functions. So one of those functions is one of. So select df. Again, let's grab this data set, and don't worry about the minus for now. We want to grab one of new col or dret. So what it's going to do is it's going to look at all the col names and say, is it equal to new col or dret? If it is, great, select it. Right? So if we did that, it would just give us new col or dret back. If there wasn't a column named new col, it would still run. It would just give us dret. But the negative says drop those. So it says select these two, get rid of them. Okay? So what I'm going to do, so one of is a special function. So again, I'm going to use the question mark and say, sorry, I did question mark one of, right? And this is the help file. And these are the helper functions in dplyr. Starts with ends with, contains, matches, number range, one of, everything. So these are helper functions that allow you to grab column names using, some sort of pattern rather than having to do something like, x1, x2, x3, x4, x5. It can be starts with X, for example. So this allows you to do similar to what you can do with wildcards in Stata or SAS. All right, ordering columns. So CN is the column names of the data frame. Now I'm going to make a new vector and give it the order in which I want to do it. So I want new column to be the very first one. df bracket rows. I want all the rows. I want these specific columns. So I want new column. And then I want all the column names where they don't equal new column. So, in some respects, we're showing you this code to kind of get you some intuition on bracketing and still logical operations over and over again, because you're going to use that a lot. This, I'm not necessarily suggesting that this is the way you should reorder your columns, because I think the next slide is much more intuitive. But the reason we're going over these over and over again is because we're saying, hey, see, you collect things, you put something in the first position, and you can subset a thing based on a condition and collect them together and then use the bracket notation. That is one way you can do it. So we're still trying to reinforce these concepts over and over again. But I think this is way more intuitive, right? Select data frame, new col, and then everything else. It'll keep the order. You see new col as first. Everything else is put back in there. So again, these helper functions are helpful. Right? They allow you to do things that you want to do with selecting specific columns. So you specify the ones in order that you want, and then you just say everything else, keep it the way it is, just put it back in there. Okay, ordering rows. This is probably one of the most important things to do along with subsetting, because we're to school of public health. We almost always have data that's longitudinal. Something where it's multiple visits, multiple things that it's sorted, that's important. This slide, this operation right here is the reason we converted everything to dplyr, more or less. This was the previous author, or it's not previous author, my co-instructor, I fought with him for many times. This is the use case, I believe, for a new user, why you'd use dplyr over other things. So this is the way, in base, how you reorder a data set based on a variable. You use the order function, you can grab the column, the vector, df $mpg, order it, and use it as a row index. And it will sort them. Let's look at miles per gallon, 10.4. So on and so forth. They're in order. This is very confusing to a new user, in my opinion. You have 10 different things going on. You have $ notation to subset. You have ordering. You have a function inside brackets. You have square bracket notation. That is row, comma, column. I think this is very unintuitive. This is the way I think, nope, that way. This is the way I think makes the most sense. Arrange the data set by this column. So arrange is the dplyr function. So again, we've talked about filtering rows, selecting columns, mutating. Oh, now we're talking about arranging. Also, we talked about rename. So this does the exact same thing. Look at miles per gallon. Miles per gallon. It is there. It's in order. So the base way, there are other options. Order, you can put decreasing equals true. It will put them in decreasing order. Okay? You can put a negative sign on numeric vectors, and you can sort this one increasing and this one decreasing. It'll go in the specific order you want. It'll sort by this one. Any ties or anything like that, then it'll sort by this one. But this one is decreasing. I still think these are not that intuitive. This also does not work for characters. If you're sorting on name or something, you can't put a negative sign out in front of it. So the way you do that in arrange, you say arrange, data frame, any column you want. It is going to be by default in ascending order, increasing. If you want it to be in descending order, the DESC function helps with that. So you say, I want to arrange this data set in descending order for miles per gallon. Okay? And similarly, like the example I gave before, I want to increasing miles per gallon. If there's any ties, do decreasing horsepower. So, for example, a lot of times what you do, arrange by patient ID and then dates, or patient ID then visit. Right? So where you want to get the data set in an order. Okay. Yes.
Is there some reason row names appear?
Yes. So that's dplyr. dplyr does that. So that's why I'm gonna show you at the end of this how to make a column name or a column of the row names. So, but that is one important reason why we showed tibbles versus data frames. Tibbles don't have row names, tibbles don't have row names. Also, dplyr functions strip row names. It's important because if you need that data, make it a column. Okay. Lastly, there is a function called transmute. It combines both mutate and select in one fell swoop. I don't use this that much. I'm usually more explicit about mutate if I'm adding new columns or changing new columns or changing columns or anything like that, and then selecting the ones I want. Transmute will take a data frame. If you want to define a new variable, you can do that, and then give it the other variables you want to keep. So note, this keeps new column because we just defined it, and these other two that we put in there. But it drops everything else out. So transmute kind of combines these into one thing to say, like, I want to make this new column and I want to keep these other columns same thing. Okay. Lastly, let's make. Okay, that is a long lecture. So row names, df, right? We got these. Somebody give me one way to assign a new column. I'm going to call it car. df $ car is equal to row names df. We have a car. So when row names are stripped off, we don't care. Somebody give me another way. All right, somebody give me a way to get rid of this column. Yep. Okay. I want car again. What is the dplyr function for creating a new variable? Mutate. So, two things. Oh, I'm going to bring this up. Mutate car equals row names df. We see them in there at the last thing. We also see the row names are now gone. Okay. Give me another way to get rid of this. In dplyr. How do you get rid of a column in dplyr? One of the ways. Select df what? Minus car. Gets rid of it. Okay. So most times though, when you use like read.csv, read_csv, that kind of stuff, it's not going to do anything with the row names. It's not gonna make a column to be row name, or it's not gonna assume the first column is your row names or anything like that. So if you're reading data in with most of the standard ways, it'll be fine. There are some reasons why row names are if you have a data set where everything is numbers, right? But everything is numeric, but just it happens to be that the first column is some sort of like label. There are reasons why you want to do like things and keep that a matrix for speed and stuff like that. But for 90% of the time, row names, make it a column and go forward with that. Don't rely on them. All right, so we have a lab. I'm going to go for a 5-minute break, but website, we start in the lab. It'll take about 20 minutes, so around 3:30. I'm going to reconvene, but the lab is on the website, and we will go over that with the key when we're done. So in the meantime, You get up, stretch your legs, do whatever you have to do. I will be around to answer questions. Okay, so if it keeps running on there, you should just be able to hit stop. Yeah, sometimes that'll happen. The data set. So filters not. So dplyr is the back here. Filters the function. So turn it. See if you can. Okay. So let's just restart that real quick and let's run the code. So let's for example, let's just run that. This all the way up. So click it, highlight it. Perfect. Run.
Yeah.
So let's. Do you have the minus data downloaded? Do you have the minus data downloaded? Let's just say df. Let's say df equals no. nt bars. Or like with letter n. T. And then hit tab. Yep. Perfect. Okay. Let's load up the dplyr library dplyr. It's already installed. So once it's already installed, you just load it up with library. You'll get that. And so you were saying df. Speaking of df, workspace. Okay. And shift n. So you can shift control. Oh, okay. So filter. Parentheses. Let's type MPG greater than 20. Yep, and let's just run that. Yeah. So just install it. Okay, so now we got miles per gallon greater than 20. Okay, so click back here. Click in there. You just get in here, so just hit the up button. Yep, and that's the last command. So let's do command shift. Control. Yep, let's say select. Let's see. Let's say here. So we got miles per gallon, greater than 20, and then we grab it. Then we filter. So we hit up. Filter the rows. So, and then grab select which those two columns afterwards. Okay? And so if you hit up, go back. And you tweak that out. So there are 14 rows that have miles per gallon greater than 20. Sorry. So DF has a bunch of bars, but only 14 of them have greater than 20 miles per gallon. so download the lab, and
So, I don't know how I did this, but when I made the car variable, it just came out as count. So, the car name. So I think I deleted it somehow, but I'm not sure how.
So right here. So that reassigned the. So when that happens, so you have to do here. So we will. So if you go up, if you do it when you assign it to the cars, you have to do it to the cars and then assign it to the car. Well, no, because DF is already changed. So you have to go up. So right here, which is DF for cars. As long as you had done it before the name was shut off. But if you run the take command, it actually will shut off. So right after you define DF. Yep. You said run it and the DF dollars on car. Is equal to Yep. And so you just have to run. You have to run these two commands again. So DF is going to be completely run. So you have to run those on. Head data here. Just down here. Yep. You just say like head data. Parentheses data. Let's get the first couple of those. So if you run all the code now, if you run this mutate command, it's going to have all the names. So, sorry. When you run this command, so let's run this command.
Are you
Yep. Okay. So that, the row names are now gone, but that car,
No, it gives
the
you
car
the
variable.
core title, but it doesn't tell you what it is. Or doesn't tell you what it is. I mean, NPG
There's not the same, there are, yeah, but cookbooks are bad.
Why?
Just the way they're made, right? Like, it's harder to export them in a lot of respects. Yeah, and the text file that you can read it back in. Like, you can't, it's hard.
It's for display.
Yeah, but kind of wholesale reassigning cookbooks are not really that great. Not really easy. I mean, they're not bad per se. R has some analog, but not something that's. If you look at the HMIS package, or something for a lot of people.
I mean, the things that you did with me, I think what the variables are, what the categories of variable are, these are pretty basic things.
Yeah, I mean, so you'd have it named as like whatever the variable is. So that's what you have. You do, conscious and smart variable. I mean, State will still have. If you don't have good variable names, then you have to go through and do describe.
Right.
So.
Oh, yeah, that's part of the reason why I'm here. Like, for real.
From late,
Label fine.
oh, so like that's in the data. So I'm saying like labeling a specific column. It's not from that. It's not from that column. But sorry, labeling the data in the column is. So I'm saying in a data set you have male or female. You wouldn't have 0, 1, and 0. You have actually just male. But like if it was a column code G, there's not necessarily. Not many people use code books to define the G column. Does that make sense? They would call it gender or gen or something like that. Does that make sense? The column. So we're talking about instead of value labels versus variable labels. Not a good analog in R for variable labels, but factors are much better for value labels. The data inside is the column itself. Yeah.
Yeah.
That's, yeah.
So.
So, at least for when we were doing this, really briefly, we wanted the lab itself. We wanted you to do some reinforcement of column names and row names, and so some of the other stuff we talked about before. So we didn't cover these yet. N col and N row. That'll tell you number of rows and number of columns of a data set. But we did cover length, and we did cover column names and row names. So at least for some of these questions, that's the way we assumed you were going to solve them, right? So I'm not going to go over it just yet, but like it says how many, you can get row names or column names, and then you can wrap that in the length to see how many there are. You can also count. I mean, we weren't necessarily say like go and count all of them, but there are some functions that we'll talk about a little bit later that'll give you a little bit better summary rather than these functions. But if you want, we didn't cover it explicitly, but we assumed in some respects if we talk about column names and row names, you should be able to figure out how many there are based on that. Listen, can you grab that real quick?
Yes, you can type question mark health, or sorry, question mark and right there. Health. Google. Yeah.
Returns them as missing.
Well, SAS.
Yeah.
You still need your variable with less than 3 existing values. Include those as the ones that
So Stata treats missing values as like infinity. SAS treats it as like behavior. R doesn't do that. You do that. So what it'll do is it'll check so what'll happen is it'll be trues and falses and misses. If you do filter in dplyr, then it will exclude those. If you can say that or there's a function is.na is missing, so you can combine those together to get the true or the misses. But by default, dplyr and filter will remove those. If you use the subsetting with NAs in base, so like row, comma, column, if you subset based on that, it'll give you back misses. So, but it will drop missing by default based on filter. So you have to still be pretty cognizant of missing data there. Usually it's condition or is that NA.
I actually see that as an NFN. I don't like in SAS. You say less than except make sure your code, you know.
Yeah, so it's the opposite behavior. We still need to check on how many rows and how many observations you keep. And then, but by default, we'll talk about this. Some of the functions, or most of the functions, like summarization, like mean, median, mode, or not mode, mean, median. If you, by default, if you have missing data, return missing. Just kind of as a caution to say, like, hey, you're missing data here. You didn't subset it, but there are arguments to say, like, just remove the missing data. Entry is 0, just says.
Thank you.
When I installed the summarization,
The sign sheet. Yeah, so we're going to go over a few things, and then about like 4 other questions, and then set everybody back off. We can take 5 minutes after that. Good to know. I'll explain that. Okay, so we're going to go over a few of these things. So I put the lab key up there. But I'm gonna walk through it. Gonna walk through it either way. Okay. Whoa, that's small. So one thing, just see if you have it. Empty cars. If you have it, it'll run. If not, you can also do data empty cars. So what class is it? Data frame. So what? So use class, right? So how many observations? How many rows? What? 32. How'd you get that? N row, empty cars. 32. If I say row names, empty cars, it'll give me all those. One, I can look, see this little bracket, 31. Okay, there's 32. I could have also put length around that. Give me 32. How many columns? Yep. So, what happened here? If I say length on a data frame, right? R counts the number of columns. So it's saying how many columns you have, how many variables in this data set, not how many rows, and not how many total, row by column observations. It doesn't do that. So when you're using data frames, n row, n col, you can also use dim for dimensions, right? Rows and columns, if you want. All right, so go to the attendance sheet. Number 4. I was going to have you make a random number selector. Okay. Hilda, you got pulled. Number 4. My command didn't work. So let's what did you try, and let's fix it. So we got empty cars. All right, everybody right now, really quick, also, Command or Control, Shift M in our studio. Okay? Did you get one of those? Okay? So we're going to use the dplyr command. So let's say select the subset. Intentionally made it confusing. Select the subset of rows in more than 20 miles per gallon. So I want to subset rows. What am I using? Select or filter? Filter. What do I want? MPG greater than 20. Okay. We got that. Gives us it back. Before we do any other calculation, how many do we got? 14. Nice thing about deleting row names, we can count just by looking at the end. Now, I think this is already loaded, yeah. Okay. Nice thing about using piping, if you open up a dplyr command, hit tab. These colors mean things. Those colors correspond to columns of that data set that you piped in. So empty cars, that's draft, blah, blah, blah. So if you have really complicated large variable names, for example, you're like, what was that called? How did I spell draft? You can hit tab, this will pop down, you hit enter, it fills it in. Okay. So, you can use piping with other commands other than dplyr commands. So how many are there? What command did we use to count the number of rows? N row. So what we did was, took a data set, piped it in, used the variable name MPG, and we piped that in, the output from that, into n row. that would look like this, or we could say hi MPG. I could have done this, grab the number of rows. We haven't showed you this yet, but this will return trues and falses, right? It's logical. Wrap that around in a sum, treats the trues as ones, the falses as zeros, adds them up. That's another way you can do it. Okay. So this is two ways. So piping, by default, it's going to say, take this thing, throw it into the first argument of this function. So here, it took empty cars, which is a data set, threw it into this function filter. The first argument filter is the data set. So it says, okay, throw this data set into this first one. Then the other arguments are, what are the conditions you want to subset on? Then this one, nrow just takes into an object x, in this case, a data frame, and it gives us the number of rows. Does this make sense to everyone? Okay.
What's the shortcut for the pipe?
Command-Shift-M, or Control-Shift-M, depending Mac or Linux, or Mac or US.
Does it change if you add parentheses at the end of nrow, or does it work?
So if there were other arguments, you could write other arguments here. Right? If it doesn't happen to be the first argument, you have to do different things. We're not going to get into that. dplyr is nice because all the arguments, all the functions, the very first argument it takes in, it is a data set. All right. Select the subset of rows that get you less than 16 miles of gallon and have more than 100 horsepower. Okay. Somebody tell me what to write.
I put filter parentheses df comma mpg less than 16 and hg greater than 100.
That's good. The only thing is, you can use df if you've defined it. If you have not, use empty cars.
Okay.
So I'll show you what happens. Okay. And then we can pipe that. We can get that. And what's it going to say? It's going to show us 2, right? MP less than, did I put 12? 16. 16.
It's 16.
16. I put 12.
10.
10. Correct. Now, how do I get it if I don't want to have to look at the data set? I want it to give me it back. Like, you can pipe it. We can put nrow. And you give us 10. We can put nrow all the way around it. Exactly. Whatever makes more sense. Now if I try this. What? So, df, I deleted everything from my workspace. df is not defined. But it still did something weird. It said, no applicable method filter to apply to object class function. But if I do this, if I say x not found. Why did it do two different things that are both not found? The reason is, x doesn't exist, says I don't know what you're talking about. df doesn't exist as a variable. But if you type in df, there is a function called df, which is the density function for an f distribution, for example. So, this is another thing I want you to note. You can make, not necessarily the greatest idea, but you can make objects that are names of functions. I can make this data set into empty cars. Right? But if I say df 0.515, once I put parentheses, R knows when you say df with parentheses, you mean the function, not the data set. Okay? So when we did this, it says call the density of the F distribution, this statistic, this whatever, degrees of freedom, or whatever that is. So this df is a function, this df is a data set. Okay? So it's okay to name things, still the names of functions. Not a great idea, necessarily. I can create a data set called filter Not the greatest idea, at least to keep things straight in your head, but R understands the difference between an object that in your memory and a function. Okay? So that's why sometimes you might get, that's why these two things give you different answers. It says X. I don't know what X is. I'm going to fail. But up here it says, hey, you don't have a DF in memory, but I have a DF function. Maybe you want to apply it to that function. And that doesn't make much sense, but R is going to try it. But what happens is it says, you know what? I can't filter for a function. That's not how these things are built. So that's what happens. So you can totally use DF just as long as you define it before you use it. Alrighty. Let's take 5 minutes. Let's take a crack at 6 through 10. So. Well, the way that you bring it, and version, it's you gotta tell it legends all. But it doesn't exist. That's why it says right. This is the dplyr function filter, and when you use filter, and you call and you use the column. That's fine, but that's it doesn't say row top. It's two. So that. Yeah. So this may cause some problems. That's a. Yeah, it should have. Sorry, yeah. So one of the things was, let's just at the top make sure we put in library dplyr. Yeah. Just so that what you had was the correct idea. Because sometimes. Exactly. Yeah. Okay. I'll do that. It might have been trying to temple. Who knows? Okay, but it might have been doing something. Well, so it's just a warning. So if you have a version of dplyr, thank you. I think so. It seems like your R version is a little bit old, but that shouldn't affect your ability to use the functions in the package, is it?
Once I try to load it,
It's fine. It's just saying that the package that you have, there are many different versions of R. The current one is 3.4. This is just saying that the current one on your system is 3.3.
if I try to use any of the dplyr functions.
If you try to use the dplyr functions, they should work because nothing major should have changed between those two versions. Okay, so we are working with columns, we know that we want to use select, which is good. And then only for the person that needs it. Yeah.
Oh, that should be okay.
Yeah, just
Well,
well,
it's
it's
just
not,
saying that one of the packages that you have,
testing for equality, you have to actually use
was built on
but that's exactly right.
that shouldn't be a technical issue.
I was gonna make sure anything.
So just saying this package built, you have this was built on a higher version, so it should work completely fine. Just if you're overseeing that sometimes. So that's installed with dplyr. Yeah. So install a new version, and that's normally the reason let's say they use something
When you run things, everything can run
that could be an issue. This
run
package
things, and sometimes objects are created you need for later commands, but that's how it's been working.
So that just ensures that the package exists underneath that package is all. It's still okay. Yeah. You don't have to do that for data sets that are preloaded into R. This empty cars is just like this kind of data set that you have for example. So that's why you don't have to do this. So don't worry about that data. You don't need to do that. Like, cause you're not gonna be using like the R data set, so you're using ones that you're reading yourself, right?
The first item is changing column name.
So you normally don't have to do that because the dplyr functions, some of them will return a TBL.
Okay, so
Yeah. So, but the one thing we wanted to demonstrate by doing this, the main thing we wanted to convey is that when dplyr runs,
okay, because
it removes roaming. That was the big reason why we did that. So
the way
you
we
never pretty much have to do this.
you want to rename a column with a tab, right?
So what I'm saying is you have to make a column that, like for example, the
No,
cars.
no,
You have to make a column in the data
this
set
is what
that
the
corresponds to the cars.
right? So
Rather
that's
than
the
line
change
row.
in all capital letters. So that's the old thing now. So one of them
So
is
I said,
switch
make this a column in the data set, right, using
So
new
you
tables.
need first.
And then you still have that column to know which one.
Is there a way to do all at once or is it?
Okay.
Oh, so now you are. Okay. To change them all.
All right, so let's go over some of these.
It'll be easier with Basear.
All right, so one thing I want to note. Okay, so I restarted my R session and I didn't load in dplyr yet. So the MT cars data set is still in memory, still in there, hanging out. But if I do try this command, I say filter, you'll get an error. And again, that is because dplyr isn't loaded up. This filter command is not the filter command that you want to use. That's one based in stats. So it's trying to do some weird temporal filtering, and it says, I don't know what these things are because this command is not one of these smart dplyr commands. So you just have to load it, and then if you run that filtering command, it'll work. So, sorry, this command. If you run this filtering command, it'll work. So,
I'm sorry, which one is it, Ron?
I'm saying make sure dplyr is loaded before doing dplyr functions. Make sure you put library, like you load the library. That's all. So normally when you're working interactively like this, it's not a big issue because you probably have loaded it somewhere along the way. But if you go back and rerun this script, make sure at the top, for example, dplyr is loaded when you run it. All right, so let's create a subset of the data that only contains the columns WT, QSEC, and HP for only the cars that have 8 cylinders and assign this object to cars sub. What are the dimensions of this data set? So let's make this. So what do I have to do? So I need to do filtering and selecting, right? Somebody give me some commands.
Car sub equals filter
Empty cars, CYL equals 8.
Okay.
And then car sub equals select, parentheses, empty cars, comma, WC, comma, QSET, comma, HP, and then I did STR car sub.
Okay. Really, before we do that, car sub is filtered. What happens in this line? Sorry, what? So we select these 3 columns.
Yeah.
But what are we selecting it from? From empty cars. So we want to make sure we put car sub in there, right? Because car sub is the subsetted one. So STR car sub is one way to get some of the information, right? It'll say 14 observations in 3 variables, right? So if we did that with empty cars, it'll probably tell us, yeah, exactly. So somebody give me a pipe. Empty cars, piping it. So we're going to say cycle equals 8, right? Yeah. Oop. Don't want to minimize. Pipe. QSEC, HP. Again, if we switch these up, will this work? No. Because we took out cycle when we selected. Yes.
So I actually done car sub equal the beginning. And
Mhm.
everything else.
Yep.
I think that works.
Yep. Sorry, I was just doing that to run that, but yes, that's how you should reassign it. And then you can say nrow car sub to get the number of observations. So there's 14. Again, also sum empty cars cycle equals 8 should give us 14 back. All right, let's convert the column names to all uppercase. So sorry, this is a little confusing. This wasn't covered. We shift around that code. So how do I get the column names of car sub? Column names. I'm going to call it CN. Right? So to upper, we'll make it uppercase. So let me show you the way that you know based on rename. So car sub, I'm going to say rename. Right? WT equals WT. QSEC equals QSEC. HP equals HP. So that's explicit. It'll do exactly what we want, right? But what if we don't want to write out every single one of them? Okay. So I cheated. I knew this command. So to upper, we'll make things uppercase. Okay. So now how do I reassign the column names? So column names car sub equals to upper. Now they're renamed. And they were renamed here. They would rename here as well. But note, I did rename the column names to the uppercase versions. If I run this, now I get an error because these column names are no longer there. They're the capitalized versions. It's case sensitive. So this command looks for a variable named WT in lowercase. And if it doesn't find it, it's going to give you an error. Right? So if I run this, let me run this command and run this right before, without running these 2 lines, without running the uppercase, it'll run fine because it finds the column name WT, QSEC, and HP in lowercase, and it assigns the new variables. Everything's good. But if you want to do it wholesale to upper to lower, this is the way you can do it. Sorry, I don't mean to keep moving around. CN is the column names. We set it equal to the uppercase of those. We could have, instead of putting CN here, we could have put this in there to have one big long command that says right, So these two will work. This will work in one line, but it's kind of seems a little convoluted. This will work, but you have to be explicit about what you're renaming them to. Okay. So reorder the rows of car sub by weight in increasing order. Okay. How do we reorder rows? Range. How do we do it? All right, so what is weight now? Capital WT. I've been jumping around so much. Let's just, okay, WT. So, increasing. It is. How would I do if it was decreasing? So, DESC. It is not that. That actually will work. Sorry. That's the... That will work with numbers. So let me show you what I mean. Cars is empty cars. I'm going to say cars. Give me 1 minute. So I want to show you now we have a column that's character, which is the actual car. So arrange cars by weight, and I didn't rename them here. That'll work just fine. But if I do that, that'll work just fine because it'll say, hey, sort the negative. So numbers, that makes sense. Characters, it doesn't make sense. But we can always do descending car, and it'll order them alphabetically, reverse order. Okay? So DESC is more robust because it can work for characters or numbers. Okay. So we just said do the same thing. Copy empty cars into a variable called cars. Rename MPG to MPG. Okay. We can use the rename function, right? That should be explicit. Rename capital MPG equals lower MPG. Somebody tell me how to do it the base way with column names.
Column names, cars, square bracket. Column names, cars equals MPG equals MPG.
Yep. So we can do it that way. Let's confirm. We put cars up there. MPG is the first one. Big capital letters, great. So that's another way you can do it. Okay. But rename, for this specific example, much easier, much more explicit. You just say rename cars. Sorry. I'm going to put head around it so we can actually see some things. So rename cars, big uppercase equals lowercase. We're all good. Subset the columns from empty cars that end in P and call it pvars. Do you not? So we showed you one of, so you got to look at the help file. So let's look at the help file of one of. So it starts with, ends with. So let's select empty cars. And what am I putting in there? Ends with. P, the string. P. Right? I'm just going to say column names. So those are the two columns that end with P. Okay? So, again, look at the help file. Go over these. They are very helpful. And if I wanted to reorder them, rather than subset, if I say everything, it'll put the ones that end in P first, and then all the other columns. So the first two are the ones that end in P. The rest are, and you can just say everything else. Alrighty. Subsetting. It's important. Head just shows me the top of something. Just so I don't print out all the rows, because with data frames, yeah, it's kind of it shows too much. Alrighty. So we're getting into some data summarization, and we're going to go through some of these, not super quick, but a lot of them are really straightforward, right? Functions that do basic statistical summarization. Mean takes the mean. SD, standard deviation, median, quantile, range, gives you a 2 numeric vector with the min and the max. There's also min and max, which will give you the minimum, the maximum. Sum will take the sum of x's. These things, every single one, okay, we will talk about missing data. If there is missing data in x, every one of these functions will return missing. If there's any missing data at all, it is a caution for R to say, hey, I returned NA because usually because of two reasons. One, it doesn't make any sense to take the mean with a missing value. You don't know what that value is. You don't actually know what the true mean is if that data is missing. The second thing is, it's to alert you to say, hey, you have missing data. I don't want to do anything that's going to screw up your analysis. I'm going to alert you that it's not going to give you a warning, but it's going to give you missing back. So on every one of these options, there are options to remove the missing and then take the statistic. But by default, if there's any missing data whatsoever, it'll give you a missing back. So there's also a bunch of transformations, everything you can think of, log base 2, log base 10, square root, absolute value, all the fun ones that you know and love. Let's see, I think we make this bigger. Yeah. So again, head over and over and over again, I show, because if the view, the capital V view function in our studio, where it brings up a spreadsheet and you can scroll around and look at that intuitively, if that makes sense to you, use that. I do not do that. I do everything back and forth with the console, and so head is my go-to to just give a snapshot, give me a quick look at what's going on, to make sure my code executed correctly and the things I expected to happen. So head will give you the first 6 elements by default. If you put it on a vector, it'll give you the first 6 elements. If you put it on a data frame or a matrix, it'll give you the first 6 rows. So again, mean and all those things expect you to put in vectors. One of the ways you can get them is the $sign. So here, mean MT cars HP will take the mean horsepower for all the values. I'll give you back 146.68. Quantile, if we pass the vector in there, it'll give us the quartiles by default. So the min, the max, 25th, 50th, and 75th percentile. There is another argument called probs in quantile. What quantile do you want? 60th, 10th, 0.1%. You just put it in a probs. You can put it as a vector, right? So if I want, the 25th, the 50th, that kind of stuff, it would be 0.25, 0.5, 0.75, 0.99 if I want the 99th percentile. Just put that in there. It'll give it back. Median, we'll take the median weight, right? Pretty standard, pretty straightforward. None of the data we're talking about right now has missing data. We didn't want to get into that, but again, if it did, they would come up NA. T-test. We're going to be covered more on later when we talk about statistics, but it is another way to get means and standard deviations. T.test. You put in a vector, one vector, without a grouping variable. It does a one sample t-test. Whether that mean by default is 0, you can give it a value to test against, but it says this is the data, this is the t-statistic, degrees of freedom, this is the p-value that this mean is different from 0. The mean of x, the mean weight is 3.21. Confidence interval is 2.86, 3.75. That's one way you can get kind of an overall summary of a vector. A lot of times you want to do that in table 1 or something like that. So, missing. Just making some sample data x here. The missing value in R is NA. Capital N, capital A. It is not quoted. It is just NA. Okay? Like true, like false, it is a special thing in R. It's defined. It means missing. There are different things for not a number. For example, if you try to divide 0 by 0, or if you try to divide a positive number by 0, there's an infinity and negative infinity. We're not talking about those. We're just talking about straight missing. R does not do what other statistical software does. Stata, infinity, missing is infinity, more or less. It's the largest value possible. SAS, it is negative infinity, right? I mean, you know, heaven forbid they talk to each other and made it anywhere consistent, but no. And then R is totally different. So, you know, so it's all different. So, but missing data, working with missing data is some of the most important things you need to know. NA is the operator in R, and again, if you say mean X, it's going to say NA. Again, to alert you to say, there's missing data here. You should know that. Yes?
So if you have a CSV file you read in, and it has blanks or it doesn't have an NA, does it get converted to NA when it's read in?
Good question. So there are NA. Okay, so the answer is it depends what options you put on the read CSV function. By default, I'm pretty sure that empty strings will not be converted to NAs in characters. If you have all numbers and an empty string, it will convert it to NA. If you have all characters or any characters and an empty string, and what I mean by that is quote, quote, there's no characters, no spaces, nothing in there, it'll remain as quote, quote. You can convert that to NA based on logical things. You can say which, column, bracket, equals, quote, quote, equal to NA. Right? So you can assign it that, but it won't do that by default. You can set some of the options to have it do that. Okay. So the way you can actually perform these operations, NA.rm. NAs removed. Remove NAs. Mean of X, NA.rm equals true. So you set this argument to true. I want you to remove NAs and take the mean. So this is the mean value. It doesn't treat them as zeros. It calculates the denominator correctly. It takes all these numbers, 157, 42, 8, 10, 45, 42, adds them up, divides by however many numbers I just said, and it's good. It doesn't divide by the length of X or anything like that. Quantile. So the difference between mean and quantile, the difference between mean, you say NA.rm equals true. If you say quantile with missing data, it just says, nah, I give up. Like, I'm not doing that. I don't know what you're doing. You have to remove the NAs yourself, or you have to tell me you want to remove them before calculating the quantiles.
So it doesn't go with the whole it doesn't go with the whole record.
Not with the whole record. At least for this vector. There are different operators that if you want to identify if an entire row has any missing data or something like that, there's a function called complete.cases, and that will come up true if every single column is not missing in that data set. That being said, if it is an empty string, just if you have an empty string for, let's say gender or something like that, that will not be treated as NA unless that is actually an NA. Okay? So there are other operators that will do things specifically on rows or columns. So row means takes the mean over the rows. Column means mean over the columns. Row sums, col sums will do the same thing, but sums. Summary displays quantile information, so I'll show you that in a second. These are really important because of the things we just said. We'll show you a way to identify NA values, and if you take the row sums, it'll tell you how many missing values are in that row. Row columns will tell you the number of missings in that column when you couple it with some of these NA operators. Okay. I will get to that in a second, but I wanted to do summary pvars, let's say. So if you do summary on a data frame, it gives you what I don't believe to be a very great summary, but it gives you some summary. So numerical things, it gives you the minimum, first quantile, median, mean, third quantile, max. Pretty much running the quantile function and the mean function at the same time. But again, I usually just run them explicitly over the variables I'm interested in. But it is a good snapshot, I would say. All right, so again, if you're using Excel files, we've had some issues on some computers. Just download the Excel file to your disk and then read it in that way using the import rather than trying to download the file. There have been some weird things with trying to download it through R and then read it in. So just go here, download it, have it somewhere. And we use the read Excel package. We're going to read in TB incidents. We're going to call it TB, and it gives us a tibble. Okay. So again, row names don't exist to a tibble. Sometimes you'll also see this backtick thing. Backtick over there. Backticks. So data frames do have a little bit of rules for how you name the columns. Generally, they don't start. They usually don't start with a number. So if it does this weird backticking thing to say, okay, this is kind of special. I'll keep the name that you wanted when you read it in Excel, but this kind of indicates that this doesn't conform to the standard rules for column names. Usually it would be like year _ 1990. And it can't have spaces. Can't have spaces is not the right way to describe it. It can have spaces, but they aren't referenced the same way. You have to use these backticks if it starts with a number or it has spaces in it. Generally what we're going to do is take this and rename the columns so that it's not something, with these backticks and spaces. So right now, we're going to call in dplyr, rename TB. Let's put the country to be that whole first long thing that the Excel spreadsheet had. So again, this is going to be a big problem if you're not. This is going to be something you have to do if you're reading in Excel spreadsheets from other people, especially because people generally like to make the column names more or less an entire sentence, which is good and descriptive, but not necessarily so great for analyses, and not good for like shorthand and referencing those things. Okay, so now we change the country name, so now the column names are country and all these years. All right, so that should be, we've covered that. So column means and row means must work on all numeric data. That first column is a country name. Doesn't have numbers associated with it. So what we're going to do is select, and we're using one of these fun operators, starts with a 1. So all the years it starts with 1, anything up to 1999, we're going to grab those. Then we're going to use our newly learned operator, col means. So there is missing data in this data set. So this is TB incidents by multiple countries. Not every country has full data up until 1999. Also, this data goes back to like 1750 or something like that. I think Britain and some of the other countries are the only ones who had it. So there's missing data all over the place. But we want to just get the averages over time. And so we put na.rm equals true. So these are the average TB incidence rates over time, actually from 1990 to 1999. And so we can plot them. Again, maybe it's not always comparing apples to apples. That doesn't mean the same number of countries are in here and here and here, but that's one way you get the averages over time. Okay? So you can also make a new column, before 2000 average. So these are just the 1990 to 1999. So now we take the row means of this data set and we remove any of the missing. Now for each country, we're going to get one number, and that's the average from 1990 to 1999 of the TB incidents. So row means gives us a vector back. We assign that to a new column in our data set called the before 2000 average. So that's the average TB incidence rate based on available data that we have. Okay? And then I'm just showing you kind of what we get. I'm just subsetting. This is just to show you the output, not anything important. All right, just kind of give us a not important about the code. It's saying Afghanistan, for example, 168.0, I think, per, let me see what it says, per 100,000 for 1990 to 1999. Okay? So now it's a new column in our data set. So again, we could have done min and max. We do summary. When you do it on a character, it just says the length, and it's a character. It doesn't do any of these summarizations. All right. So we're going to talk briefly about apply functions and grouping data. So apply functions will, or the apply function will apply a function, do a function over either rows or columns repeatedly. So it's kind of like a for loop. It goes to one column, does something, goes to the next one, and so forth, or it goes to one row and does something, and then goes to the next row and calculate and computes that function over and over again. So the the arguments are apply X, an array including a matrix, right? So this can also be a data frame. Margin, so margin, you either usually put 1 or 2. 1 if you want to go over the rows, 2 if you want to go over the columns. The way you remember that is you go back to subsetting. What is the first index in subsetting? It goes rows, comma, columns. Rows is 1, 2 is column. So 1 indicates rows, 2 indicates columns. The function to be applied. So if we said apply, So if I said apply averages to mean, note we're using the averages data set because if we do this over each row where we had some character data, you can't take a mean of that. Right? Where we had the country names, we can't do that. So we're using the averages where it's 1990, 1991, all the way to 1999. So, 2 means I want to go through every single column. And I want to take the mean, and I want to remove missing. This is exactly equivalent to running column means that we were talking about before. This just happens to be a lot slower. This is slower. But this is to demonstrate what we're doing. Matrix or data frame with numeric data, numbers, by each column. Function, it just happens to be mean. If we wanted median, we could have done that. Here we do standard deviation, here we do max. So these are the column standard deviations, the column maxes. Right? So the mean for 1999 was 125, the standard deviation was 126, the maximum was 695. Okay? So apply what you put in there, which margin, 1 being rows, 2 being columns, then the function. And then, afterwards, you put any additional arguments to that function. What I mean by that is this na.rm corresponds to SD. So again, it's X, margin, fun, and you'll see this a lot in the help files, ... So this says these are optional arguments, so it'll be defined in the help file. But these are additional arguments to pass to this specific function. So apply doesn't have an argument called na.rm. Apply says, take this, go over the columns, use the mean, and then we're going to pass this argument, na.rm, to mean or standard deviation or whatever, just so it knows to remove standard deviations. To remove missingness if it's there. So there are other apply statements, and I would say a lot of seasoned R programmers use these a lot. Tapply, sapply, lapply. We will talk about these two. Tapply is kind of a grouping apply. We are not going to go over that because we're going to talk about grouping in dplyr. So right now we're going to finally use that youth tobacco survey for something. We're going to read the data in and call it smoke. All right, so it's youth tobacco smoking. So unique will give you will return the unique values of a vector. So let's say you had IDs. Unique ID will give you just the unique IDs in that data set. So here, we're grabbing unique, smoke, location description, 1 to 10. We just want to see which ones we're looking at. So these are the states. And also some national levels. That's what's in this data set. So length, coupled with unique, will give you the number of unique identifiers. So in this case, we have 50. It doesn't correspond to the states, not all the states. I think Alaska and Hawaii are not in there, but we have a national estimate and some other estimate in there. So you get a round number of 50, but it's not exactly states, but you can think of it as states. So location description essentially is states. But here, if you want to say how many RDs in this data set, length, unique IDs, Table. Table you'll use a lot. Table you put in a vector, table things up. You generally don't want to do this with a continuous variable, right? Because that'll be a whole bunch of unique values. So what it'll do is it'll find the unique values and then count how many there are. So this is just a standard frequency table. So table, smoke location, and I'm just showing the first 5. So there are 378 records for Alabama, 240 for Arizona, 48 for Colorado. Okay? So we talked about unique. Table is very, very important. So this is a frequency table. When you want to do, we will talk about table where you put two vectors in there. For example, table x and y, where x is the treatment variable, y is a categorical variable, and you get a two-dimensional table where you can run Fisher's exact tests on there, chi-square statistics, that kind of stuff for table 1, for example. All right. So we're going to do some filter. So I'm going to filter the data set. I only want the variable, the measure for smoking status. I want the overall gender, and I want response equal to current. So we looked at this data. We already had done, some exploring to see these values. But this data, subsmoke, has the smoking status for all genders that are current smokers. Yes. Yeah. I think I forget what the actual response is. Or it's how many cigarettes, that's what it is. So we've filtered on the rows that we want because this data is long. It's got multiple records per kind of state. So we want to take the data, subset the columns because there's a lot of columns in there. We want to take the year, the location description, again, you can think of that as state, and the data value. So this is kind of I think the number of packs per day or something like that, or cigarettes per day smoked for the overall. That might not be exactly what measure it is, but the idea is our data has a bunch of rows, but one measure per state. Okay. So tapply, I'm going to do this very briefly, but the idea is this exists. People will give you answers for this online. It allows you to do an operation where you group by something. So in this case, we are going to take the data value. Let's say it's cigarettes per day. We're going to group it by another variable, in this case, year. And we want to take the mean. So this is the mean over all the states of cigarettes per day. Okay? So X is thing you want to do the computation on. Index is the grouping variable you want to go over. So the reason I don't cover tapply that much is okay. If you want to do grouping things, which you want to do many, many, many times, especially with long data, especially with repeated measurements, especially with longitudinal data, you want to group things together. So group by is the function you want to do. So in this case, we're taking that data where it's only I believe the cigarettes per day. We want to group it by year. We just happen to choose year. We could do year and state, for example. We could have just done state. We can group by as many variables as we want to. And then we are going to group this data. So after we run this command, this data is grouped, right? And it's going to be a tibble. And I mean that, it's specific. I say that because data frames don't have this grouping idea. So it's grouped together. It's grouped by year. So when you do a summarization, it'll do that by year. So the way you summarize data is with the Z or the S. So Hadley is from New Zealand. So almost all of his functions have the Z or S kind of versions of them. So I actually use and the color can be with the U or not in most of the plotting functions. But the way we do it, so we group the data together and we pass it into the summarization. And the way we do it, we say year average. So this is a new variable that we're going to create in this summarized data set, and we want to take the mean of the data value. So this is a variable in this data set. And so now, before, if we had just said mean of the data value, it would have given us one number. but because we have grouped it together, it gives us a number per year. Okay? So group by defines grouping variables that when you do summarizations and computations, it will do it holding those grouping variables consistent. So you can also pipe with it. So this is a little bit cleaner. Take the data, pipe it into group by. I want to group it by the year. I want to summarize. I want to create the mean. I could have put multiple summarizations, year average. I could have put a comma, year median equals median data value, so on and so forth, to create the summarization, the summarized data that I wanted. In this case, we just chose the mean. Okay. So really quickly, data, you group it, you summarize it. If you want to get aggregations or summaries over things. So standard statistics can also be calculated. Tally. Tally's all, so there's another function called tally. So if you group something and tally it up, it'll tell you how many it'll essentially do a frequency table based on that grouping. So let's say you group by gender and age category, and then you ran tally, it'll give you all the combinations of age and gender that exist in the data and how many records fall into those categories. In this case, we grouped it by year. Tally will do that, but it's a shortcut for essentially summarize, where n is equal to this n function. So n with parentheses counts things. So how many are there? So we group it by year. We use summarize. We create a new variable. We felt like calling it n. We could have called it whatever we wanted, number of observations. And said it's equal to this n function. And so now, it seems a little bit convoluted in some respects, but the idea is it goes through, groups it by year, and counts how many records fall into that category. And it would have as many columns as there are grouping variables, and count them. Count the groups. If you have multiple groups, it'll count if you have multiple grouping variables, it will keep those in there. So if we group by year and state and then tallied it up, it would give us all the combinations of year and state. So this tally and summarize, where you just count, are the exact same thing. Summarize can do more things. So we could have counted and calculated the mean and standard deviation, so on and so forth. Tally is just when you want to count them up. All right, so we're going to talk about a lot more visualization later, but we're talking about some of these exploratory summarizations because I think they're really important. So if you do plot x comma y, you'll do a scatter plot by default. There are ways to make line plots. Box plot, y tilde x, and we'll talk about this type of syntax, but it'll do a box plot of y against x. X will be on the x-axis, y on the y-axis. Hist of x will give a histogram. Density will calculate a kernel density of x, and if you plot this object, it'll give a plot of the kernel density. Okay, so plot. We have to pass in x and y. They're vectors. So we put in the miles per gallon, x miles per gallon, y, I don't know, I think it's the display number of years or something like that. So this is the relationship. Now, I'm sure a lot of you have heard, use R. It makes really great plots. Right? By default, it doesn't. But it makes them quick. It makes them they are very customizable, but a lot of times when you're doing data exploration, it doesn't matter making them super nice because you're trying to get a gist on what the relationship of the data is. You're trying to identify outliers. You're trying to identify patterns. So yes, this is not the most visually pleasing. This is the default plot. You have to change it to make it better if you're going to publish it. But if you're trying to say, what's the relationship between these two variables, it is 100% sufficient. You might have to do a little bit of tweaks if, for example, there are hundreds of thousands of points. There's going to be a lot of overplotting, but we can do some other plots. Hist. Remember we calculated the before 2000 average. It'll do a histogram. Frequency counts on the y-axis, x categories or x values on the x-axis. You can change you can change it with the number of breaks. There's an argument breaks if you want to do 20 breaks, 30 breaks, or actually define the breakpoints that you want to look at. So sometimes when you plot, you don't want to look at just points. So plot takes an argument called type. P is for points, L is for lines. So we're plotting the smoking average per year versus the year average. So over the entire population that we have, for all the states, this is the year, this is the average. So we do see a decline in the smoke, I think the number of cigarettes smoked. And we see it with a line, we don't actually see it with points. We could put P and L together in a vector and it would give us points and lines. Density, if we want to do a little smooth histogram, you say density, you put the vector in there, it gives you a kernel density estimate, you plot it, this is what it looks like. The bandwidth is chosen based on some criteria. You can change on how it chooses the bandwidth and that kind of stuff, but you can think of it just as a smooth histogram, and you're off. So, box plot makes box plots. So, y tilde x. So this is the y value, this is the x value. So here we're putting in the location, y we're putting in the data value, so it gives us a box plot at every single location. All right, so Alabama, Tennessee, Wyoming, so these are the box plots. If you just put box plot and put in a vector there, it'll just give you a single box plot. Another way you can do this is you don't have to do the dollar signs and all that kind of stuff. A lot of these functions take a data argument. So kind of like the dplyr functions where they're smart and they know that these are columns in your data set. If you say data equals your data set and do y tilde x, you don't have to put the dollar signs like we had before. It knows that this means they're columns in that data set. But it doesn't matter if you don't put data in there. It's going to assume this is something in your data in your environment. This is something in your environment. Plot those. So pairs takes in scatter plots of matrices. Matplot does scatter plots of two matrices. I don't use these that much, but pairs will do all pairs of the. If you put in one matrix, what it will do is it will do all the columns and do a pairwise scatter plot of all of them. There will be some symmetric things, so there's a lot of redundant data here for some odd reason. Usually, if you put, if you're more than like 5 to 10 variables, this isn't that great. You can change the dimensions of the figures so you can make it more seeable, more viewable. But we will have some other ways to make scatter plots a lot better. So base R has some apply statements. dplyr has some more intuitive syntax. Group by is very powerful. A lot of times what you're doing is you're combining that with summarize. The matrix stats package expands on some of these things. So right now in R, there's column means, column sums, row means, row sums. The matrix stats package kind of expands on that to do like row standard deviations, row variances, row counts, row whatever, more or less. So column means doesn't exist in base R, but if you do load up the matrix stats package, it has it. Okay, so what we're going to do, we're going to do the lab. We're probably going to go through maybe half of it and probably do the other half tomorrow. So should be on the website. So for the homework, I believe, I'll double check tonight, but I believe saving and that kind of stuff was some of the things you need, and we went over that today in the beginning. Yeah, and I'll post. Well, that's fun. The lab is the key. Well, okay. Don't look at the answers. I mean, you can. It's not like you're not learning. But it's no longer the case. I've taken them away, yeah. Yeah, but we'll probably go over for maybe 5 minutes, or maybe like 10 minutes, so maybe let's say around 4:55, we'll reconvene, I'll talk about like the first 5 questions, and then we'll go over the rest of the lab tomorrow, first thing. I don't think it had all the answers, just had a lot of them. That's right. That file should be substituted already. switching to CSV. Excuse me? So it's read R. Yeah. So has everyone been able to read in the data? Okay.
You have a certain number of unique types, and then you print them out and you don't have that same number, isn't something off? Shouldn't I? Yes, because I'm getting to the byte type, I'm getting 8, but then when I look at there's only 7.
Do the unique again. Not the length unique, just unique.
No, anyways. Okay.
Yeah. So we will talk about it. I'll show you the. All right. So I'm going to go through 2 of these real quick so we can move on, and I want to talk about something about reading CSVs in. So we did have a question, what happens with empty strings? So that option over here in read CSV, you see that NA is equal to an empty string, or if it's NA, right? So if you change that to just be NA, it'll keep the empty strings. So I just opened up the CSV, right? These first 3 things have nothing in them. There's empty strings. Now, that being said, I'm going to close that. When we actually view our data, use view bike. We see that they're missing because of the way read.csv reads things in. Empty strings, it treats it as NA. If you don't want that to happen, you have to change the defaults. And what I mean by that is you could say NA equals NA, where you say only if it says NA, say it's NA. Otherwise, empty strings, just keep them as is. We're not going to do that because usually empty strings are NAs. So some people said they were having some trouble with getting the data in. I don't know why that was the case, but if you just download it and read it in straight from your computer, it should be fine. So how many bike lanes are there currently in Baltimore? We said you can assume each observation row is a different one. So you can either do n row, dim. Some people, sorry about that, some people like to go to their environment, see that there's 1,631 observations. It's one way, right? Of those who live in Baltimore, I think you can be sure that that's not true. There are not 1,631 bike friendly areas, depending on how you define the city or what you define as a bike lane. But that's what the city says, so that's what we're going with. So how many feet and miles of bike lanes are currently there in Baltimore? So we want to take the length and we want to add that up. So if we take sum, we'll get that data, right? So that data is in feet. We can divide by feet to miles to get that in miles. So these are relatively straightforward. These are two different operations. Either we can divide every single element by 5280 and then sum it up, or we can sum it up and then divide by 5280. They both will work. This will perform as many operations as there are, right? It'll do length each single observation. It'll still be fast, but it'll do this division. This will only do one division. So sometimes there's like efficiency things, but at the end of the day, there's about 439,000 feet or 83 miles of bike lanes. Baltimore City. So these first two, reading it in, checking the rows, that kind of stuff. Sum. Straightforward. Make sense? So here's one thing that we did. Okay, if you use table on bike type and use unique on bike type, you'll notice something. What do you see? What's different? I mean, table obviously does a frequency count, but what do you see different between these two? NA. Table, by default, doesn't do anything with NAs, doesn't include them. So look at the help for table. So, if you see defaults like this, where it says use NA, no, if any, always, the first argument. So, let me step back. Sometimes you can pass in a vector or something, but a lot of times these are different options, right, for different behavior. The first one is the default. So it says don't use NAs, don't like them, don't need them. Okay? Unique says, hey, give me the unique. Right? So, depending on what we talk about, there's either 8 bike types or 7. If we count the missing one as an actual bike type. We can count that as unspecified, as other, right? Which one way we might be able to do it. So the answer kind of depends on the question. Do we treat on how we treat really bike type? One way we can also do use NA if any, right? Let me go back. One of the options was if any. So if there are any NAs, put them in there. Then the other option is always put NAs, no matter if there are any or not. So if we do that, what do we get? We get there's 9 missing bike types. Okay. So, there's 9 observations that are missing bike type. That's what I mean. So if we do length unique, we get 8. That includes 1 missing. Okay? So again, there are 2 correct answers depending on what you do with the missing data here. Depending on why they're missing. If they're actually just another bike type or they're an unknown bike type and you want to count them, there'd be 8. If not, There's 7. There's 7 known byte types. Let's say. So we didn't talk about this. Is.na. What do you think is.na does? See if it's an NA or not. I'm going to put unique in there. It's going to come back true when it is NA, false when it's not NA. Okay? So is.na is a logical test whether something is a missing value or not. So we talked about logic today. So one last thing I did want to touch on is we did say not equal to, right? Not equal to, like x is not equal to 5. So there is one more operator that we didn't really touch on, and that is just the not operator. So, or the negation operator. So all it does is take it takes true things and turns them false, takes false things and turns them true. Okay? Just flips them up. Normally that wouldn't sound like too important, right? Not x equal to 5 is the same thing as x not equal to 5. But when you want to say something like is.na, it's important when you want to say which ones aren't NA. That's usually what you're more interested in, not an NA. Okay? So we will cover this a bit more, but I just want to say there are operators to test for missing data, and the one thing, there is a negation operator that if you have trues and you want to flip it, it will make them false. And also, if you say again, if you use a logical operator, here I'm saying, is something equal to contraflow? Missing values will come back missing because we don't know. That value we don't know. It could be contraflow, it could be not. It's missing, still missing. So we can't know anything about this logical test. But if we want to make NAs false, we say, is it equal to this? And is it not an NA? That's how we can build a logical test that gives us true for the condition and makes it false when something's an N. And then what I was actually saying before, which we will talk about tomorrow, the percent in percent operator takes something on the left and see if it's in the list on the right. So let's see, if I want to say is that in that or bike lane. So is this value in contraflow or bike lane? So make this bigger. It'll come back true for the cases where it's in this list. So in this case, number 7, number 4, come back true. So this percent in percent operator gives us logical trues and falses. Anything that's missing, it's going to assume to be false. And it'll allow us to test for multiple things rather than a bunch of or statements. All right. So we're going to cover number 3, and then we're probably going to wrap up. So how many types of bike lane are there? So let's say there's 7 or 8. What is the longest average bike lane length? So use this t-apply. We take the length. This is the thing we want to compute an operation over. We want to do it over type, and we want to take a mean. So it doesn't, missings are gone. So which one has the longest one? I think it's side pad. Side pad. Also, we can group the data by type. Here, I just wanted to do a count. We can also take the mean of the mean length. So here, it kind of does it in one fell swoop. Both the operations that we were talking about in this question. It says how many are there and what is the average length. And then we can sort this by which command? Arrange. Yep. We can arrange this descending or so let's sort it so we don't have to use any brain power to like compare things. Arrange mean. We could do it descending or we could do it ascending. So side path has the largest average length. Okay. So does this set of operations make sense? So we counted, did some sort of frequency table of sorts, calculated mean length, arranged them so they would be in some sort of order. We got the data. So we will cover 4 through 7 tomorrow. I will still post the key. Do you want me to post the key? I guess. Yes, no, maybe. I got a yes and no.
Totally yes.
Totally yes. That was an emphatic yes. I think that wins. All right, I'll post it. So, we know how to rename data sets. We know how to get data sets in. We know how to get data sets out. We can do some manipulation. We haven't done, everything and anything. We haven't done models. We haven't done that many visualizations yet. We'll cover them. Okay. So up until now, is anything just completely off the wall? Like this doesn't make any sense.
Will you have the slides for the percent in the last page?
That'll be covered tomorrow.
Okay. It's a little bit fast.
No, yeah. So I'm just breezing over certain things, but we'll cover them in more detail tomorrow.
Can I just the one overarching thing that we talked about earlier that I don't really understand is if I regularly get data set of 1,000 variables.
Yes.
How do I even begin to look at the variable list and see what's there and what I want to use and to subset it down to the 10 that we'll use?
So so it depends how. Okay, you have 100,000 variables.
Oh, I just made them.
I mean, let's say that. Okay, so how do you know what like V002 is? I'm asking in the data you get.
I work with data, so I write a code book and I read
But it's not in Stata. I'm saying like usually you get it in some sort of flat format, like a tab delimited or something.
Yeah.
So there's a code book. As long as you can read that in. So what I'm saying is let's say there's a code book that says like a general code book that's usually variable name description, right? You can read that in just like any other data set, right? It's hard to link that to data, but I'm saying if you want to say like, I know what I'm looking for in this, you can subset that based on the criteria, based on some string matching and stuff like that, and then it'll just subset that to like, let's say 10 variables. Then you get the column of those variable names, and you apply it, right, to this data set. Granted, so there is a package called hmisc that will do what we were talking about. It will allow you to label a variable, right? So I mean that it's like if you had sex or gender, male and female, not labeling sex like male or female. I'm talking about labeling the variable name as something. So what I'm saying is code books usually are done in a way they're treated just as data. So I'm saying like you have 100,000 variables, and so so in Stata, for example, how do you know which ones you want to grab?
Well, I might have like 20 variables sort of describing sort of the same behavior. Let's say some sort of say smoking behavior. There's 20 different ways to ask me that question. And I want to read through them and figure out which one I want to use.
So what do you mean read through them?
Well, look at this one is how many cigarettes you smoked in an hour, and this one's how many you smoked in a day.
So you should have in most large surveys they'll have a code book that you can read in, or a spreadsheet or something like that that's formatted in a way where it's variable description. So
Just to go to the documentation.
yes, but that documentation should be in a readable format and not like a PDF. At least if it's a well formatted study. That's not to say that's always the case, right? But if you did have a code book that somehow you got into some tabular data out from Stata or some other software, you can use that in a very similar way to any data set in R, right? It's just now it's one column is the actual variable name, second is the variable description. And then you can do, things will show later, like pattern match, like you want to say anything that says this word in the description, subset those so I can take a look at them. You can do that, right? Does that make sense? Where you do, yeah. But it's just you name your variables well, you know, right? That's what you, like, so you know what they are, but they don't, like, that's kind of the way it's usually done, right? Or, yeah.
Would you be able to export the variable labels from Stata to?
The variable, what do you mean by, so,
In the same example we have like the DHS data set and we have several labels.
so the DHS itself has an ASCII and a dictionary file. So that's what you should be reading in versus the Stata.
Okay,
But I'm saying, but yes, but in Stata, if you have variable labels or value labels, the value labels you should be able to export, right? You should outsheet that using a CSV. But the variable labels, not so much. But they should be labeled in a way where you know what the variable is, right? Well, they should. I mean, why not? But I'm saying like a variable should never be named V0005.
That's what it's named.
Then I'm saying without a code book. That is, I mean, that is not a data management practice to name something that's incomprehensible without an associated code book. That's what I mean. So the code book should be able to be read in R and translated similarly to like data so that you can subset based on that criteria. That's what I mean. Does that make sense?